We mention the angle theta 1 as N theta 1 E. N for the theta 1, the value of theta 1 and east.
I request all the participants, please mute your mic. Otherwise, disturbance will be there in between the talk. So I request again, because I given this facility to all the participants. So please don't unmute your mic unless it is not necessary. Okay, thank you. Sir, shall we start?
Yeah, I'm ready. I'm ready.
I am waiting for the participants, and recently I have
Yeah,
dropped him
please,
asking.
please.
Okay, sir, thank you. So, dear participants, good morning to all of you. It's a great pleasure. Professor A.M. Kuthe from VNIT Nagpur is with us. So, participants, already our speakers have already covered the different aspects of additive manufacturing and or 3D printing, and most of them have talked about the applications of 3D printing in different domains. So, biomedical engineering is one of them. So today, sir will give you the inside knowledge of 3D printing in the biomedical domain. How can it be? How can it be useful in 3D print? In biomedical domains, and how can we utilize 3D printing techniques to make some medical device? So before inviting sir for the talk, let me give some brief introduction. So Dr. A.M. Kuthe is presently professor in mechanical engineering department and head of CAD/CAM Center at VNIT Nagpur. So, sir has begun his career in 1986 after Bachelor of Engineering in Mechanical from Government Engineering College, Amravati, India, by joining Hindustan Aeronautics Limited (HAL) Nasik. Then he obtained his MTech from IIT Roorkee and then joined Birla Consultancy Services as senior software engineer. Then he left the company or that particular service and joined VNIT in 1993. Then he earned his PhD in 2001. His research is mainly focused in the area of rapid prototyping. So using computer-aided design as base and specialized technique of RP, he dedicated his efforts in harnessing this technology for practical use. So the capability of RP equipment were extensively exploited to be custom-built metallic implants that were implanted in human body by surgeons in several complicated medical cases, including some cases of cancer. So the technology was effectively used in engineering industry to develop zero defect pattern making and casting. So he has, and also he has earned one patent, unpatent for niche work undertaken by him. So his contribution to international and national journals, presentation of paper at international conferences, and authoring the book demonstrated his deep study as well as authority on the subject. So creation of well-equipped CAD/CAM center at BNIT speaks volume of his passion for raising the bar of academic standard. So his self-motivation for introduction of industry-oriented courses, guidance of PhD and MTech students, as well as unitizing efforts in creating awareness and building capacity for large-scale adoption of RP using CAD is a testimony of his work in this area. So the all-encompassing contribution of his in the area of RP expands the conventional boundary of the research. So with this, now I invite sir for the talk. So sir, please now I hand over the floor to you, sir.
Yeah. Thank you, Dr. Narendra Kumar. Am I audible?
Yes, sir. Yes, sir. You are audible, sir.
Yeah. And I have already shared the screen just for the testing. So hopefully I can straight away take you to my screen.
Yes.
But before that, let me first extend my thanks to Dr. Narendra Kumar and the NIT Jalandhar for inviting me again. In the month of July, I have delivered a lecture, and then again they have invited me in the December. That itself is a very challenging job for me, because I was thinking, like, if there are the same people in the audience, they will say, okay, oh, I already seen that, I already heard of Professor Kuthe, so what else new thing? So that's why I have to rather work hard to see that something different is offered to the audience. And the interesting thing is that the topic which is very close to my heart, like 3D printing, and that too its application in the medical domain. Nowadays, I think everybody is very much concerned about the health, and the health sector is given due importance not only by the individual but even from the government sector also. So how best this 3D printing can be used in the medical domain? So that's what exactly I am focusing my speech on. So let me share you my screen, but before that, let me also inform you the good news that recently I can share my screen. Hopefully you can see that. Recently I got the patent granted for the work on the 3D bioplotted composite scaffold made of collagen and treated hydroxide tricalcium phosphate for the rabbit tibia bone regeneration. So that actually gives us more energy to talk about how best this 3D printing can be used in the medical domain. So I'm going to talk about all these things in my presentation. So let me now share my slides. So can you see my slide now?
Yes, sir. Yes, sir.
Yeah, sure. Thank you. So the topic, which is titled as the 3D printing in innovative medical devices. This is something which is very important nowadays, not only in India but all over the world. So I hope everybody is safe and taking care at this moment. So this is the our institute, and the CAD/CAM center is one of the major so-called our center in the Vishweshwaraya National Institute of Technology, where we execute all our ongoing research projects related to the computer-aided design and computer-aided manufacturing. And it's a perfect center where you will find that there is an amalgamation of the engineering and medical sciences. So I rather invite all of the participants whenever they will get, once this pandemic is over, to do visit our CARICAM center, or I will find out some event later on once the pandemic is over to call all of you there. And before that, I'm thinking of preparing one video file, virtual video file, rather the presentation of the video through video, our CARICAM center, and that I will definitely pass on to Dr. Narendra Kumar, which can be then passed on to the audience.
Okay,
So let me tell you what exactly the methodology that we are adopting as far as this 3D printing in medical domain is concerned. We are closely associated with the DM Institute of Medical Sciences, Wardha. This Wardha is a small town, not a small town, it's a district near to Nagpur. And there, this is the DM Institute of Medical Sciences, is the medical institute where we are closely associated with as far as this particular work is concerned. I particularly feel that without the help of the medical institution, it is really very difficult to carry out any work related to the 3D printing in medical domain. And therefore, those who are interested in 3D printing in medical domain, they should first identify the medical institute of medical sciences where they can actually work with the doctors. So this institute and VNIT together, we have doing wonderful work related to the 3D printing in medical domain. So what's an outline? Outline is innovation in medical device, that is number one. Number two, I have written no metallic medical implant. So I'm going to talk about this, what exactly this particular outline talks about. Then the bioplotter as an extension of 3D printer, and then research that we have performed at VNIT, and finally the conclusion. So let me quickly show you what exactly we need to look at when the innovation in medical device is concerned. Now let data speaks about it, and hopefully you will find that the data shows something very different figure, and which is somewhat figure which we need to look at. Now if you look at the medical devices import in India for the last 5 years, say from 14-15 to 18-19, the data is available, you'll find that it is continuously increasing. And you know, it if the figures is in crore, it has jumped to 38,836 crores. The data for 1920 and 2021 is yet to come, but you'll find that it is continuously increasing. So that's a big concern for all of us. Now, if you look at what type of the import we look at, so there you'll find that the category wise, the various values of the devices which are imported is indicated. So there you'll find that the electronics and equipments, they go up to 66%, consumable around 9%, then the IVD reagents 8%, implants 7%, disposable 7%, surgical equipments 3%. Now look at this figure very carefully. As far as the electronics and equipment are concerned, maximum share is in that particular slide. And this is a high-end technology, especially if you look at the machines like CT scan, MRI, then the dialysis machines and all that. They are all coming under this particular category. And there you find that the percentage is tremendously high. Yes, that is true. But let us look at the other part of it. Now, purposely, I am not talking more about the electronics and side of the equipments there, because that's a high-end knowledge. Hopefully, the India is not matured enough to get the details about that particular knowledge or the practice that particular knowledge, or even the ecosystem is yet to be established. And hopefully, that is the reason that we have to go for that. But let's look at the other part. the consumables, IVD reagents. They are all the, the category where we can definitely work on. But I am more interested in the implants. That also significantly high, around 7%. And when we talk about the implants, it is all about the medical metallic implants. And therefore, we'll have to look at this metallic implant. As soon as it comes about the metal, it is a job of the job of the mechanical engineer or the materials engineer or the engineer in general. So, implant is one of the area where I will be more interested in focusing on. And top of it, what exactly the takeaway message, that is more important. So this data is very important. Let's see the another interesting things. Let the data speaks about when we talk about the innovation. Remember, there we are always linking innovation to the patent. Now this figure is again very interesting to look at. You'll find that the country-wise patent filing in medical device sector in India. I hope you can see my cursor there. I have what the first things talks about country-wise patent filings in medical device sector in India for the period 2005 to 14. So almost 10 years the complete data has been collected. The figure depicts dominant of IP filings of about 80% of the total by foreign applicant. So foreign applicants are actually filing the patent in India, those who are not having any manufacturing base in India. This is disturbing. So the 80%, and in India contribution is only 17% of IP filings in India only. So this needs to be looked at very seriously. Why? Because when we talk about the patent, as I already mentioned to you earlier, we talk about innovation. So when patent and is not being filed in India, that means the innovation is not happening to that extent. And other people are entering into our market by filing the patent, and hence the problem will be more complex in long run. Because if at all I would like to develop some instrument, naturally that instrument is already been having a patent in India, so it will become difficult for me to start the manufacturing base, or rather start a manufacturing industry in that particular. So import substitute, that is what we always talk about. That also to be taken with a pinch of salt when this particular figure is looked at. So this is very important, and all engineers or all of us together, not only the engineers but the engineers and doctor community should look at it very carefully. So and we'll have to find out some solution to that. So let us look at that, because engineers always give the solution when there is a problem. Now think about the implant. As I already mentioned to you that we will be focusing more on the implants. So there are the two types of the implant, as I mentioned to you, customized versus standard implant. Now here, if you look at the figure of the standard implant, which are very much available on the shelf, especially the hip implant and the knee implants are very popular. And I am showing you here the customized implant that has been manufactured for the patient who is required to have the implant which is not available on the shelf. So what exactly the customized implant talks about, what exactly the standard implant talks about, let us look at it very carefully. In short, I will say standard implant which are available on the shelf, you can go and purchase it, and the customized implant is to be developed, it is to be designed and then manufactured, and that implant is to be fitted into the patient body, and that is required only one in quantity, because that is only required for that particular patient. So we had to rather look at these both part, like customized and standard implant. Let's start with the standard implant. Now when I already mentioned to you earlier that the standard implant, when you talk about, there is a stiff competition with manufacturing from the developed country. And yes, true that, and there's a big question mark here, that why there is a stiff competition from the manufacturer from the developed country. The standard, the quality of that particular implant may not be possible for us to rather meet. And hopefully in long run, what happens, like as the people are, or the doctor community are using this particular implant for the long period, they have developed a confidence in that particular implant, and therefore whosoever wants to enter into this particular market with the standard implant, naturally he faces a lot of problems. I don't know how many of you people are aware of, but Sri Chitra wall, a heart wall, which is used in cardiology. You know, in cardiac surgery, when they use the Sri Chitra wall, it is one of the best invention by Dr. Valiathan, and it is being used extensively. But look at the Sri Chitra wall. There are competitor from the developed country, and what I heard that the Sri Chitra wall is very much in demand in Sri Lanka rather than in India. So the developed countries, they always gives you the stiff competition, and whether it will be possible for us to remain in this particular race or not, it's very important. And therefore the standard implant is always taken with a pinch of salt whenever we talk about the fabrication or the manufacturing of that. No doubt we'll have to look into this, that we have to upgrade the whole method, a technical field in India, to see that the standard implants are also manufactured in India. And in that respect, I would like to just give you the reference of India 2035, which you people must be aware of. Like India 2035 is the vision document which is been prepared by the TIFAC, which is available on the Google. You can just go and see that document. There they are mentioned that by 2035, the indigenously manufactured passenger aircraft in India should be possible. So think of that, you want to go somewhere out that is abroad, and there are two planes. One is manufactured by the Boeing, another is manufactured by the Indian company, and you are free to take the ride on any one of that. So this is what they say, that by 2035 we have to build the quality of our manufacturing sector to that level. If that is possible, hopefully we can think of by 2035 we can have even the standard implant manufactured in India. And that's how one of my orthopedic surgeon, who is a close friend of mine and is serving in the in Bombay as a oncologist in orthopedics, he said that we wish to rather see the day when the orthopedic surgeons in India, they are demanding the implants made in India, and they rather than the implants manufactured from the developed country or the imported implant. So anyhow, that is what is our wish list. Hopefully we will do that. There are n number of rather the parameters that we need to look at. But look at the 3D printing. Now this 3D printing, as you know very well, and you people have already, you must be going through the lectures in this particular FDP. So it's very simple. This is a self-explanatory figure, CAD file to slicing to STL and getting then the physical model. Now this 3D printing is used with the computer tomography, which you people are already aware of. They call it as a CT scan. So this computer tomography and rapid prototyping works on the same principle, that is computer tomography slicing, rapid prototyping layer by layer, and it is possible to rather shift the data, rather get the data from so it is possible for you to get the data from the computer tomography as an output and give it as an input to the rapid prototyping machine. So this is a wonderful figure which actually shows how you can transfer the data from the CT scan to the RP machine. So this is an RP machine. Look at my cursor. Then through the RP machine, it is possible for us to get directly the medical model of the part which you have scanned. So here I am just showing you the femur bone, and then this can be used to manufacture the metallic part or the metallic implant. So this is an implant manufacturing using RP. This is a wonderful methodology that is very well practiced. I am going to show you about all these things. So this thing is possible So 3D printing can be used for manufacturing of metallic implant. Okay, let me show you quickly the one or two case studies that we have already done. This is about a customized implant, which I always used to show to the people that how this particular, if you look at again my mouse, you'll find at this cursor that this particular implant is manufactured by the surgeon and our team together, and there we have actually executed how the through the RP the model, and then giving the doctor getting his idea about the implant, and maybe through the clay model, the reverse engineering, then again RP, all this methodology that we have followed to get this implant which is manufactured in metal, and this we have fitted into the patient body. So the patient who was suffering from TMJ for bony ankylosis, this is a temporomandibular joint, that is what they call it as bony ankylosis. Once we fit it with this particular implant, she was a lady, she was in a position to open her mouth. So this complete detail is available in the paper. You can refer this Rapid Prototyping Journal, volume 17, number 5, 2011. And it's a wonderful work that we have done it as far as the customization is concerned. Now this is only possible because of the 3D printing. Let me show you this another interesting example. This is about a malignancy, that means a cancer patient. Now in this case, we have actually developed the customized implant for the mandible which is affected by the malignant tumor. So this one is being resected because this is a malignancy. So resected, then this particular implant is manufactured again by using the same methodology, the way I told you in the last slide, and finally we have fitted into the patient, and you can see the patient when before the operation and after the operation. This is completely written in the Journal of Maxillofacial Surgery, volume 71, number 2, 2013. So you can look into these two papers, and it will be interesting for you to rather see how we have executed this particular methodology. What exactly I will be more interested in this particular cases is that these are all customized implants, and we need to look into this particular domain. No doubt, as I already told you, standard implants is always there. We need to rather look into how the standard implants can be developed. But let us focus on this customized implant. So this particular project that we have completed in 2014, wherein it was shown that how exactly it will be possible to rather develop the customized implant by using the rapid prototyping, 3D printing, the medical imaging, and the manufacturing route. Here we have taken the casting route by using the simulation software and all that, and finally use it. So complete methodology has been shown that how it will be possible to develop this particular joint replacement implants. So this we have taken it for the hip implant, and this we have shown it, and this is one of the project that we have completed in 2014, and that's actually has helped us in taking what is called as a leapfrogging as far as the use of 3D printing in medical domain is concerned. Now let me go to the next point, and that is what no metallic medical implant. So let us look at this figure, a very interesting slide. Here I mentioned no, and everywhere I mentioned yes. So this is a contradiction, and that's why I have specifically shown you this particular no. Why yes it is? It is because we do talk about that the metallic medical implants are having problems. I'm going to talk about that soon. But the other than metallic medical implant, there is always the problem that you can't rather think of any other thing than the metallic medical implant at this moment when there is a load bearing implants. And therefore, though we say that there are problems with the metallic medical implant, but that is the gold standard still today available, and you will find that many cases, if you go and visit any factory, any hospital, where you will can see the hip implant surgery or the knee implant surgery and all that, everywhere they are using these so-called metallic implants. Now there, what you will find is that this metallic implant, they do have a lot of problems, but still we have to use it because that's the only standard available at this moment. So what should be done? That is what is our next important point. But no doubt we will be required to look into the customized implant. That is what I am slowly rather narrowing down your focus. But ultimately the metallic implant are also required to be looked at from the problems that is associated. So what are the problems? So look at this particular figure. I have mentioned in metallic implant an interesting so-called term which is used. They call it as a stress shielding. Now this stress shielding is very important, and I wish to rather talk about this from the engineering aspect and the medical aspect both. Now look at, this is a hip fracture, and once this gets broken, you know, you will have to put the metallic implant. So now this is a wonderful figure. If you look at the cursor, that this metallic implant with the cobalt chrome alloy and then the titanium so-called shaft is inserted into the bone, which is having a cortical bone which is very tough. Then there is a marrow, that means so-called the canal, and there is a cancellous bone. Now this cancellous bone, this is very soft, and this is cortical bone which is bit hard. But look at this particular figure and you will find that this is an interesting, rather the combination from engineering point. We have the so-called metal here, which is having a high Young modulus. Then we have the cortical bone, which is having the Young's modulus much lower than the metallic metal, like a titanium or cobalt. For example, cortical bone has around 18 gigapascal and titanium go 125. So you know, this E is different for titanium, E is different for cortical bone, and if you look at this cancellous bone, then the E is very less, and so it's a composite structure where you have the Young's modulus from high to low, okay, and high-low combination. Now what happens in such scenario? I am just showing you here. Look at the other figure where a tennis player is shown, and he is using his hand to rather play the ball. So you know, when they have actually seen the bone of tennis player of their hand, they found that, that's what I have shown here, the figure. They found that in one hand the bones are bigger compared to the other hand which they are not using for playing. Now why this happens? It is because when bone is stressed, or when the bone is given the more and more rather the exercise in one area, then it starts growing, it starts strengthening, it develops. But if at all it is not used, then they call it as bone resorption. That means bone loses, bone slowly gets loose. That means it actually vanishes. That's what they call a resorb, this bone resorption. Now that's what exactly happens if you look at this particular implant. Now here, this is a metallic implant, and this is a cancellous bone and a cortical bone having a Young's modulus much less. So what happens, whenever the load is transmitted, then this will be taken up mostly by the metallic part, and the soft part will not take more load because the Young's modulus is more there. So naturally it is taking more load, and then what happens, the cortical bone or the cancellous bone rather is not taking more load. So what happens, because it is not taking more load, it starts resorbing. Resorbing means slowly getting loose. That means vanishing. So now this leads to what? This leads to what is called as implant loosening. So I am just showing you here the interesting picture that this particular implant is fixed into the hip, and this is actually a metallic implant, and you will find that this gets fitted into the femur, but as the load gets transmitted continuously through this metallic implant, the slowly the bone get resorbs near to that and it will start loosening, and that's what exactly this particular lady is facing the problem. So this is one of the major problem that we'll have to look about in case of the metallic implant. Now look here, the whenever a metallic medical implant is fitted into the aged people, they always say that you keep your activity low, don't use that. But if the same implant is used in case of a young people, generally in young people, you'll find that the productivity get affected of that particular young person. So that we don't want to happen. And this is what I am rather more interested, because we have rather started with the customized implant. So when we are developing the customized implant, naturally we'll have to take care to see that ultimately that implant doesn't get loosened. So all this thing is very important, and I hope you have understood why I have written the no there. That there is no other standard than the metallic implant at this moment, but at the same time, in long run, it may affect. And that's what they say whenever any implant is fitted. They say that, okay, you may have, this implant will last for say 15 years. It may happen that if you increase your activity with that particular implant, metallic implant, the life of the implant will be less than the 15 years. And that is why we'll have to take care. How exactly to solve this particular problem? We need to, I hope you have understood the problem that is required to be looked at. So here you'll find that the next point, that is what I will be more interested in, that about the bioplotter as an extension of the 3D printer. Okay. So what is the next one? That's what we talk about, the scaffold fabrication. And remember that how exactly the implant is to be manufactured. I have just given you quickly the two references of the papers which you can always look at, and you will come to know how exactly the metallic implant can be manufactured. But because of the stress shielding and the loosening, we'll have to look at the other interesting area, that is called as the scaffold fabrication. So that is one of the earliest application of this 3D printing, which we also call as rapid prototyping, and now it has become a more successful and mature area. As I already told you, that because of our work which has been accepted by the Indian Patent Office, we found that yes, a lot of work can be done, because that is all related to the animal study. I am going to talk about this soon. So this is one of the interesting area. Look at this bone scaffold, to which we also look at, rather title is tissue engineering. Now tissue engineering is one of the interesting area where, so you can see that it is mentioned that there are problems whenever there is a so-called defect, which is large defect, and in that large defect, the metallic implant, it is also mentioned here that it causes the metallosis. Metallosis is nothing but an infection because of the small metal that gets released in the system. But that part I had purposely not discussed here, because that is not related to rather what is important here. I have told you that important is implant loosening. Now see here, the scaffold is fabricated, and what exactly we do, look at this particular figure. Here you will find that this is a large bone defect. Look at my cursor here, large bone defect. Here you can actually fit what is called the scaffold. Now what is scaffold? The scaffold is nothing but, actually it is a mesh structure of the various materials which are biocompatible other than the metal. Remember, though we do use the metal as of scaffold at this moment, because that is not been matured enough with the other scaffold like a ceramic or the polymers, though we are starting lot of research is being done all over world. But scaffold is nothing but a mesh structure, and ultimately this particular mesh structure or the mesh is fitted into that particular bone defect, and the cell starts seeding or rather developing into the bone tissue. That is what exactly the bone scaffold is. Let me show you this interestingly what exactly is being done. So this is the body where we need to feed that. So we take a CT scan, then ultimately send it to the our system. Then using the instrumentations, which is possible for us to scaffold a bone fabric scaffold. Then this scaffold is then finally rather tested and then fitted into the patient body. So this is a RP assisted scaffold fabrication that we have done it earlier. But then we have rather shifted to the another interesting area. So this is about the first part my PhD student has done using the 3D printing using FDP, the FDM, the scaffold fabrication and all that. Then later on, we have actually procured this particular machine called 3D bioplotter. Now, 3D bioplotter is very, very important, and I'm happy to tell you that there are only two installations at this moment. One is at IIT Kharagpur and another one is at VNIT Nagpur. Now, this 3D bioplotter is an interesting machine which we are rather procure to develop the scaffold. Now, using this 3D bioplotter, it is possible to develop the scaffold layer by layer. And that is why we always rather looked at the 3D bioplotter as an extension of the 3D printing machine, which we are using. I hope you people must be rather learning in this particular FDP. Basically, there are the three types of the 3D printing. One they call it as a liquid based 3D printing. Another one they talk about is a solid based 3D printing, and third one they talk about a powder based 3D printing. So all these three types you must be rather looking at. Where so the 3D printing generally we classify in this way, or we classify in another way also. Like we say that non-laser based 3D printing and laser based 3D printing. So to make it simple, so that you can understand it clearly in first go. So non-laser based 3D printing is rather cost effective, and I particularly advise to the institute, those who are interested in starting their research in 3D printing, to first go for the non-laser based, and then you go to the laser based, because the maintenance and the other part in case of the laser based is rather somewhat complicated, and it should not happen that we have procured a machine but we are not maintaining that. So it's like getting a car and then not in a position to maintain that car. So the all pleasure that we wish to have of the car, that will not be there. So it's exactly like that. So first start with the non-laser based system, especially the FDM machine that we have started with, and then later on shift it to the laser based system. So this 3D bioplotter is actually an extension of the 3D printing. Here the material used is the ceramic or any other material of which you can make a paste, and then ultimately this material to which we call as a biocompatible. That's why it is called a bioplotter. So this material they are developed or this particular part is developed layer by layer using the biocompatible material, and that is what exactly the scaffold fabrication. It's very interesting. I would like to just show you quickly one of the case report that we have done it, and it will be of more interest to me, though you may not be in a position to read the whole text. But here I have mentioned to you that the mandible case, which has been identified as a carcinoma. So this particular, how we have treated it by using the image processing software like Mimics, Rematic and all that, including even the surgical guides. So this is the simple 3D CAD model of a mandible, and this is affected region of the mandible is also shown, that this is where you will find that the problem is. Ultimately, we have resected that particular part by using the first customized scaffold design using a thematic software. We have also designed the surgical guide so that it will be easier for the surgeon to cut it in the right position wherein we need to fix up the implant. And then using the 3D bioplotter, we have developed the scaffold, and layer by layer. And this particular scaffold, this is what the different types of the scaffold that I am showing. And here we are used 0, 45, 90 degree, 135 degree. This is the actually the so-called laying down patterns of HATCP. HA talks about hydroxyapatite and tricalcium phosphate. This is the scaffold. So it's a ceramic. So this we have developed. And finally, using the FDM assisted disease mandible and mandible CSOG, everything was well tested. And finally, this is being used in the surgery, and the part is being fitted into the, that means that particular implant is fitted as a whole surgical procedure. Sorry for the blood and everything that I am showing it here, but actually I wish to show you that what exactly is being done by using this particular scaffold fabrication. So this scaffold fabrication is interesting because I would like to just show you that how the various, what are the studies that we have done, and rather how we have looked at the selection of the stand orientation of the scaffold development. And you will find that if you look at this particular complete result, though it is somewhat disturbing at this point for you to, because you are looking it for the first time, but I would like to tell you, take you to the one, here you will find that this pattern 0, 45, 90, 135, this is the best pattern that we have found, and this we have actually used in the fabrication of the scaffold and putting it into the patient body. Let me tell you what exactly this particular pattern is all about, because everybody must be interested in knowing what is this 0, 45 and all that, Look at this particular pattern, A, B, C, D. I think that will give, that will help you in. So it's a laying down of the so-called the layers. So the first layer is laid with the maybe horizontal or 0 degree. The other layer is at 45 degree. The next is 90 degree, 130 degree. So this is a layering the material in a so-called different orientation. And if this has been done, and you can get actually all these things first on the computer software, and then that particular pattern you can send it to the 3D bioplotter. 3D bioplotter will mimic the same. So everything has to be done first on the software and get the things done. So these are the various patterns which we have actually executed, and then we have seen that how it will be possible for us to get the scaffold with the different layout pattern, and that actually gives an interesting result for all of us from the mechanical point of view. Remember here, they are all the pores which are related. They are actually the through and through pores, and in that pores slowly the cell will start developing. So this is what is an interesting thing. Here you will find that the problem of the impact loosening that we have seen in case of a metal implant is almost eliminated. It is because slowly the tissue will start generating, and though I think I don't have the enough time to tell you about all these things in one go, but what is interesting to look at that this extracellular matrix, that is what we talk about the scaffold, slowly get degraded in the body, and you will find that the complete bone implant made of bone gets formed. So that is what we talk about, bone is replaced by bone. That is what is actually expected in medical literature, and this is what we are approaching at. So without engineering support, it will not be possible for the medical fraternity to achieve this particular task. Okay, so quickly I would like to show you what exactly the research that we are doing and we are proposing in VNIT. So this is a bone tissue engineering at VNIT, where we will be, I'm just showing you the cycle. I don't want this cycle to be completed because I don't want a healthy individual to meet with an accident or become a patient. So the patient, if at all there is any problem with the bone fracture, large bone defects, then you have to take a CT scan. CT scan. Then you have to take a CAD conversion here, that is medical imaging software. And here I am showing you the 3D bioplotter. Now this 3D bioplotter you can use to develop the scaffold. Though I am showing it here with the stem cells bank and with this all the seeding and then incubating and developing the scaffold and all that. But nowadays even the stem cells are also not required. We straight away fit it into the patient body, the scaffold, and you will find that the inbuilt cells or rather the natural cells are available. So no need to take even the stem cells. And finally the testing and then using that scaffold in surgery to make that particular individual healthy individual. So this is what the bone tissue engineering at VNIT, the research we will be presently executing, and we are getting a very good support from the DM Institute of Medical Sciences at Wardha. That's what I told you right at the beginning, that this is interesting, that if at all you want to enter into this domain of the research of 3D printing in medical side, you will have to first find out the medical institute with whom you can closely work. And if you have, this is a combination, if you get the good medical fraternity to work on that, that is what exactly we do want. We do want that every hospital should have a manufacturing unit of the scaffold, because they are all customized scaffold. That is what we are targeting at this moment. And you will find that if every hospital is having the manufacturing unit of the scaffold fabrication, that's what is the ultimate aim, and every patient will get the benefit of the knowledge that we will be generating. So this is again the same slide. My student is working on that. I would wish to tell you that what he has done, like he has actually developed the various models of the scaffold. He has actually done the various tests, cytotoxicity, skin sensitization, even animal trials, clinical trials to the patient. Then we have done it with the regulatory one company. They have helped us in animal trials. So this is what exactly the lab where we have done the animal trials. So this particular one is developed the in vitro cytotoxicity, and the rabbits that we have used for the skin sensitization. And finally this we have fitted into the rabbit. That's what we talk about, the rabbit tibia bone implantation model that we have fitted into the patient in the rabbit, and we have got a wonderful result. This result we have rather published, and you will find that these are all the animal, the right and the left leg, then what happens where there is a defect and we put the scaffold, and if we don't put the scaffold, so ultimately it's a wonderful result that we got it. We have done the histology section of the control specimen. I think engineers may not like to have all these things looked at, but these are all required to be done, because ultimately we'll have to use this in the patient body as a live patient. So this histology report is actually received based on what we have done, and we find that the scaffold that is being developed, put it into the rabbit, is doing has given us a wonderful results. And you'll find that that's what you can see, that we are written animal 4, 5, 7, 8. I'm just quickly showing you this slide, but this is all about the wonderful result that we got it. And then you'll find that once this is done, rabbit tibia bone implantation, and we found that the results are very, very promising. And that is what I told you, like 0, 45 degree, 90 degree, and 135 degree. That's the pattern that we have used. And you will find that with this rabbit tibia bone implantation result, we got our patent. That's what I have shown you at the start. And this one, we have then even used it in some of the clinical cases at the IMS Wardha. I would like to quickly show you about these clinical cases. So this is the first cranial surgery attended at DIMS Varda. This is in case of a cranial surgery, you know, I'm sorry that some of you may not like to see such a complicated photos, but I think to make your idea more clear, this is important. So you can see this particular figure. This is interesting that whenever a cranial surgery is done, so the skull is removed by making the burr holes. Now this once the operation is over, this same skull is been fitted, but you know the skull cap is sutured like this on the holes which has been first drilled, and you can see the drill hole, and this is the suturing. So these drill holes remain as it is. I think you can see this. Why this drill hole? Because to remove the skull and then operate on the brain. So this burr remains as it is. So we have actually fitted the scaffold in that burr holes, so that even that burr doesn't remain, that hole doesn't remain as it is. This is what they generally do. They keep it as it is. Slowly they look at how it will get developed, and we want to see that it gets the bone gets developed or regenerated in that part. So this is how we have done the first cranial case surgery. We got a very good result. What we have concluded that generally after the 40 or 50 years age, the bone regeneration in the skull side is very less, and therefore the use of the scaffold helps in regeneration to some extent. This is the another one which I already told you about the patient who was suffering from the cancer. So I have already mentioned to you about this particular case. Then these are the dental cases that we have done, around 4 dental cases, wherein the socket preservation for the post implant placement, and it has got a wonderful application in dental side. So dental surgeons also find it very, very interesting. And these are all the cases that we have actually used, and we found that the result is very, very promising. What is interesting here to look at that the scaffold is replacing the metal, and though it is taken with always very carefully, but you will find that the bone start regenerating very fast once the scaffold is put into that particular area. So this is what exactly interesting part. Now I'll be more interested in telling you other than the what clinical stages that we have done. Now what next at VNIT in tissue engineering? Though we are now manufacturing the scaffold, giving it to the hospitals to get it the result of the clinical case studies, and ultimately use it in the so-called for the data generation. Now we will be also we are also interesting rather in tissue engineering, where we are starting using the AI, artificial intelligence. It is because you know human intervention is to be minimum, or rather almost nil, because this is a very high-end area in medical women. You know, the medical device that we are talking about in this particular say talk is the class 3 device, which is high risk device. Class 1, class 2 hardly there is any problem, but with class 3 device you have to be more and more careful, because these devices are actually inside the body, and therefore there are a lot of objection on such devices, because it may lead to infection, and that infection may pass on to any organ of the body that may lead to some problems in the patient body. So we want to rather use the AI. We are actually working on that particular area. We have submitted the proposal along with the Swedish universities, and this we will be finally entering into the domain, or rather wish to enter into the domain, where we can actually prepare the organ in vitro. Remember, there are two things: in vitro, in vivo. So in vitro means so it's like, if I can say in a simple word, lab development, a lab developed organ. So now look at this particular graph, you'll find that the waiting list, especially for the organ, is increasing day by day. Though this is indicating of the data from the US, we don't have even the data from India. You'll find that the waiting list is continuously increasing, and the donors are less, receptors are more. So naturally, the many deaths are happening because there are no organ donors. Can we solve this problem? The answer to this is yes. In long run, if we can use the tissue engineering the way we have started using it in case of a bone, so it is possible to extend this area to other organs also, that means to the soft tissue also. And there if you can use the AI, where the human intervention is minimum, hopefully it will be possible to get the in vitro organ, that means organ developed in the lab, which can be straight away fitted into the patient body, and this problem can be solved. So this is what we are presently working on in the VNIT. That's what I told you, that please do visit and see what exactly we are trying our best, because the 3D bioplotter is giving us interesting results. So finally the conclusion, I hope time is almost getting over, because I need some more time for the discussion also with the people. That's what I told recently in one of the meeting in AICTE, where they have just asked about the opinion of the resource persons in the ATAL courses. So I told them that the 1.5 hour is really wonderful, because with 1 hour presentation, later on if I get a half an hour discussion, I think that actually gives something more from our side. So that's why I generally keep some 10-15 minutes or minimum half hours for the discussion. Finally, the conclusion is, it should always link with the so-called some takeaway message. This is a project that presently we are executing at VNIT in CARICAM Center. We call it as a BETIC. It is the nickname. The complete name is Biomedical Engineering Technology Incubation Center. And here you have to look at this particular model of the BETIC. This is a define, then the develop, deliver and deploy. Look at only the one which is shown with the here define, then develop, then the deliver and deploy. So this particular model is what we follow. Define means we define, rather look at the problem, and problem we actually take it from the doctor, and we involve the doctor right from the first step. This is what is very much required. I have seen many people working in the medical domain, but they contact the medical fraternity, especially the doctors, maybe after working on their research, and finally rather not getting a good response from the medical fraternity. So I think this should be avoided. And that's what I told you right at the beginning also, that if at all you are interested in starting any work related to use of 3D printing in medical domain, the way we have done it, as I already mentioned, first look at the doctors who are ready to help you, ready to cooperate you, ready to work with you. And if you can get such hospital and the doctors, I think you are almost achieved 50% in your success. The rest 50% is efforts from both sides. That means from medical domain and from your domain. So that is what we talk about, the define. Then we develop, where, as I already mentioned to you, in case of a temporomandibular joint, that how we interacted with the doctors, then how the doctor has given me the so-called clay model. Ultimately, we use it, clay model, to actually test it from engineering aspect, and then we have manufactured it and then put it into the patient body. So that is how the develop starts. Then the deliver, that means the industry should be in a position to rather manufacture your part, or you may start your own industry, and that's what is nowadays the need of the hour. And then finally the deploy. Deploy means rather put it into the patient body finally. So unless it is deployed, that research is of no use, and that is what we always take care in BETIC research. We say that we are using that particular research to see that the patient gets benefited, society gets benefited, and that is what exactly our BETIC project is. So you can visit our BETIC website. So in conclusion, I will say that make in India for medical implant, that is very much important. And that is what I told you in my first slides, that why there is a need of rather make in India. Maybe that's what I told you. We focus only on the medical implant as a engineering first. Maybe in long run we'll have to enter in not only into the customized implant but maybe the standard implant together. And if we can do that, I think I would like to repeat it again. What my friend orthopedic surgeon has said, wish to see the day when the orthopedic surgeons in India are demanding the implant only from India and not from other country. So this is what exactly we do want. Then there has to be strong academic linkages of all the institutes, not only the ISCs, NITs or the IITs, but even other institutes should also get linked to share the human and material resources, because the job is tough. It is no doubt important, but it is tough. So naturally we'll have to share the human and material resources. I am very much happy to tell you that two of the institutes here in near to Nagpur, they are always taking our help to get the some help as far as the software is concerned. They use our 3D bioplotter also, our 3D printing machine also. So that's what exactly the sharing has to be executed. And finally, the innovation process, that means first from bed to bench and then again back to the bed. That means the problem should be identified from the doctor, then get that particular problem solved. That is what we talk about the bench. And once you get the problem solved, you have to see that that particular problem is solved for the patient, and that means the solution is obtained, the patient is getting benefited through this particular aspect. So I hope this is what I wish to tell you as a conclusion part. Thank you very much for the patience hearing. My email address is amkme2002@yahoo.com. You are free to contact me anytime. As I already told you, once the pandemic is over, it will be my interest, or rather I'll be, it's my standing invitation to all of you to please do come and visit us. That's what I always used to say in many of my lectures, that I always like the advertisement of that घड़ी detergent टिकिया, पहले इस्तेमाल करो फिर विश्वास करो, exactly like that. Please do come, see what we are doing, and then I think you have to believe or not believe. That's interesting, not to look, not to talk about. But if you get inspired to work in this particular domain, I think I have achieved everything, whatever I wish. Thank you very much for this. So I hope.
Thank you so much, sir. Thanks a lot for this wonderful talk. Sir, you have covered all most possible aspects.
Yeah.
Medical manufacturing, the medical terms, even some queries are there. Like for you to get response.
Yeah, it will be my interest. Yeah, please, sir, please.
One of the query asked by the Santosh Kumar, he's saying that respected sir, 316 stainless steel coating throughout through PVD can be possible for polymer part, like in biomedical application. He just want to know about.
Yes, the coating is in another area as far as the implant is concerned, and a lot of work has been done on the coating. Generally, what is the need of coating, especially for the so-called osteointegration? If you talk about the metallic implant, we do want that the bone cells should get attached to the implant, and therefore, you know, not only the metallic coating, but the ceramic coating is more popular. And ultimately, in case of a metallic implant, when you have this type of a ceramic coating, then that actually gives you a wonderful osteointegration. But again, you know what we are presently looking at? We are presently looking at the high difference in the Young's modulus of elasticity of the metal and the bone. So we would like to match the elasticity, modulus of elasticity to that of the bone, and that is what our main focus is. So a lot of work has been done about the coating in the biomedical center at the Sri Chitra Institute of Medical Science Trivandrum, and this coating is the work is also being done in the Ceramic Institute and Calcutta also, but ultimately a very costly process, very complicated process, and top of it, the ultimate aim to achieve that the implant will not get loosened in long run. That is what is need to be addressed, and that's why we are entering into this tissue engineering side. Yeah, I hope I answered it.
Thank you, sir, for your clarification about the query. Sir, another query asked by Rupita Ghosh. She is writing that how can we manufacture graded scaffold through 3D printing?
Graded scaffold. That means if at all she talks about the pattern that I have shown, it's very much possible, because 3D plotter works exactly in the same order the way 3D printer works. You know what you do in the 3D printing, you actually get the CAD model, and this CAD model you rather send it maybe in the form of a STL file to the 3D printing machine, and you will find that the physical model is possible. Exactly in the same way, you have to work on the system with the softwares that you do have with the bioplotter. You can have the various pattern changes, and even the layer thickness also can be set, and if you can then send this to the 3D bioplotter, it will give you exactly this physical model. So we have tried it by using a different materials also, not only with one material scaffold, but the different materials in the same scaffold. Even that has been also tried, because there is a provision in such in this particular instrumentation. So the work is on the software side. So if you work well on the software side, I think getting a physical scaffold is very much possible.
Yeah, thank you so much, sir, for your response. Dear participant, if some more query you want to ask, either you can write in the chat box, so I can read them for you to the sir, okay, so that sir can respond. Either you can raise your hand so that I can unmute you, so that you can directly ask your query, if any.
Yeah, it will be interesting.
Yeah, Sudhakar Naka, yes, he's asking about please throw more light on in vivo and in vitro. Secondly, the layered process, whether is it 0, 45, 90 angle from the base?
Yes, I'm really happy that this term in vitro and in vivo, the first one, what the participant has asked. This in vivo talks about inside the body, and in vitro talks about outside the body. Now here, what we are required to do is that whatever the procedure that we follow outside the body, we call it as a in vitro. And whatever we carry out in, whatever actually happen inside the body, we call it. Now this is really very interesting. I'll tell you why. It is because when we will be actually getting the scaffold fabricated, that is in vitro. So we'll have to be more careful, because there are chances of infection, and that's what I told you, like we are interested in entering into the domain of the AI and all that, because there should not be any infection, because once you have that scaffold ready, then you put it into the patient body in the surgery. Now that becomes then the in vivo. So if at all any infection passed from in vitro to in vivo, then the whole procedure of implant fabrication and everything gets failed. So this is one interesting point. Secondly, about the layer, as I already told you, yes, 0, 45, 90, all these things you need to execute the software. The bioplotter will faithfully follow whatever the pattern you are giving as an input to that particular machine. And there you'll have to be more careful, because once it gets fabricated, then you will have to test it also, that whether the pore size is sufficient, because if the pore size is very large, then there may not be any tissue regeneration. If the pore size is very less, then there will be again problem with the cell to multiply. So what is the correct optimized size of the pore? All these things is actually studied well in advance, and lot of work is being done, and there is a lot of scope also as the research in this direction is coming. Yeah.
Thank you, sir. Thank you very much, sir.
Okay. Thank you, Sudhakar. Nice.
Thank you, sir.
Yeah.
Thank you, sir, for your response.
Yeah.
So I hope most of the queries I think already been responded by you, and the most of the broad terms and um, the common queries to the participant have already been covered by you, sir.
Yeah. Thank you. Thank
Yeah,
you.
yeah,
So, and my email address is always with them, so they
yeah,
can
yeah.
always write to me. I will be more happy to rather answer their queries. And this is what we can call is that is a starting point. We
Yeah.
are now connecting, and let us see that we remain connected forever, to see, because ultimately, this helps India to progress in long
Yeah,
run. So
exactly, sir.
we
Exactly.
need to look at that aspect. Thank you.
Okay, thank you. Thank you so much, sir. Thanks a lot. We feel pleased to have you over here for this technical session. Thanks a lot, sir. Thank you so much.
Thank you. Thank you. So should I leave?
Yes, sir. Because
Narendra?
yeah, yes, yes.
Thank
You
you.
can
Thank
leave, sir.
you.
Yeah. Thank
Okay.
you.
Thank you.
Yeah, so dear participant, our first talk of today's session is over now. So within couple of minutes, our another talk will just start. So you can have 1 or 2 minute break at your places. Okay, so Professor Sajan Kapil from IIT Guwahati, he will share his views on the research areas related to the 3D printing. Okay, at IIT Guwahati, he is doing very great job basically in the field of the metal-based 3D printing, hybrid 3D printing, and all. So let's see what he will exactly talk today's session. Okay, so in couple of minutes, he will join us. So the second talk of today will be done. Thank you. So please be here.
Dr. Narendra, good morning. Can you hear me?
Yeah. Very good morning, sir. So, sir, we are just about to start. So, yeah.
Sure.
Yeah.
I'm here.
Yeah. So, dear participant, it's our privilege and honor to have Professor Sajan Kapil, sir, from IIT Guwahati for this particular session. Before requesting Professor Sajan Kapil, sir, to start his talk, I would like to share some brief about him with you all. Dr. Sajan Kapil completed his master's in computer-assisted manufacturing from IIT Guwahati as well as from University of Stuttgart and PhD from IIT Bombay. And after that, he joined the Department of Mechanical Engineering at IIT Guwahati as an assistant professor. If we talk about his research areas as broad, so it includes the 3D printing, manufacturing automation, CAD/CAM, etc. At IIT Bombay, he had developed an additive manufacturing process called hybrid layered manufacturing. In this process, he had simplified the manufacturing of complex geometries by generating both 3 and 5 axis metal deposition tool paths. Presently, he has published about 20 plus articles in different national and international journals of repute. He has 9 Indian patents in his account, and he has also presented his articles in more than 20 plus conferences throughout the globe. So till now, dear participant, you have been shared by our experts about the polymer based additive manufacturing, and but in this particular talk, you will have an overview and the classifications of additive manufacturing in terms of metal based additive manufacturing concepts. So, sir, yes, you are requested to start, sir. Please.
Thank you very much, Dr. Narendra, for the nice introduction. So, very good morning to all of you. I think my slides are visible and I'm audible.
Yes, sir. Yes, you are very clearly audible and slides are visible, sir.
Okay, thanks a lot. So, actually, I may not be able to see the hands raised in between. So, I request the participants, if they have any doubt, feel free to interrupt and we can discuss in between as well. Okay, so like Dr. Narendra has already introduced myself, Sajan Kapil, I am from IIT Guwahati, and today I'll talk about the metal additive manufacturing process. So this is going to be the content of the lecture. I'll discuss about additive manufacturing briefly in the beginning, and I'll talk about the ASTM classification given for additive manufacturing, and then I shall discuss about the powder bed additive manufacturing, powder feed metal additive manufacturing, wire arc additive manufacturing, wire beam additive manufacturing, and then in the end, if time permits, I'll discuss about our laboratory, which is called as Rapid Manufacturing Laboratory. So additive manufacturing basically refers to layer by layer fabrication of 3-dimensional physical models directly from computer-aided design. It is an automatic process of manufacturing objects like parts, prototypes, tools, and even assemblies directly from their CAD models without any cutters, tools, or fixtures specific to the object geometry. So for example, I'm making a diagram over here. If I consider a cylindrical object and it is having a, for example, 6 mm hole over here. So to produce this part, you will definitely go for lathe machine, right? And you will do turning and drilling operation. Preferable fixture will be a 3-jaw chuck, and then you will prefer a 6 mm diameter drill bit to make this hole. Now just simply, if I just say that instead of a cylindrical object, you have a rectangular or cuboid structure. Okay, like this. Now the 3-jaw chuck may not work. You need to change your fixture, and the diameter of hole here is maybe also 8 mm. So also the tool will also change. So that is why when you go for the conventional manufacturing operation, the fixture and tools keeps on changing based on the geometry of the object. While in the case of additive manufacturing, whatever the shape is, it is going to follow the same principle. What is that principle? It works on this principle, which is shown in this diagram. We start with the pre-processing. We take the CAD model. The CAD model usually prepared in the CAD packages like SolidWorks, CATIA and all, where we represent the boundary by utilizing the accurate nonlinear curves such as B-splines and Bezier curves. We represent the outer structure or outer surface of the CAD model, which is called as BRAM, boundary representation. Okay, once we have the boundary representation of the CAD model prepared in a professional CAD package, we used to convert it to the tessellated model. Why tessellated model? Because when the 3D printing or additive manufacturing was invented, along with that, a file format called STL was also invented. It is a universally acceptable file format, which is very, very fundamental in nature, and anybody can read it very nicely. So I'll give you, for example, if you have a SolidWorks, you just save your CAD file in the form of, there are two formats for STL, binary and ASCII. Save it in the ASCII format. What you will see is each triangle is represented by 3 vertices and 1 contact normal. So these vertices are written like XYZ, XYZ, and XYZ, and the facet normal corresponding to each triangle. Why triangle? Because triangle is the 3 points can uniquely define any plane. We know that. That is why the triangle is a minimal entity, consists of the minimal topology like 3 points to represent the surface uniquely. So the surface, the boundary represented, which is usually prepared by the CAD model, is now then converted to tessellated format, which can further utilize for processing. What we do after that? We do the slicing of the CAD model. The slicing of CAD model is nothing but the intersection between these triangles and the line. And this line is corresponding to the Z height at which we are going to slice. So mathematically, you see how simple it is. You have 2 coordinates corresponding to each line of the triangle. What you want is nothing but the intersection between 2 lines to get the intersection, and that will be nothing but the points. The collection of these points which are intersection will form a contour, and that is what we get in the intersection of each slice. So for example, if I slice this sphere, I'll keep on getting the circles, the circle of larger diameter and smaller diameter. That is the only change in this particular part. Along with that, we need also consider, we have seen the tessellation and slicing, we need to also consider in pre-processing the support mechanism. So for example, if you see this diagram, if the droplets are falling at the center of the substrate, then there are no issues. It will be nicely supported on both the ends. But if the droplets are deposited on the edge, as you can see in this diagram, the gravitational force may not be sustainable with respect to the surface tension force. If it is sustainable, the droplet will sustain and you will get a small amount of overhang. But if it is not, then the droplets will fall down like this. They will roll over the object. Okay, so I think this bottom bar is disturbing. So let me, yeah, now it is. So it will roll down like this. In that case, what is happening? In this case, the gravitational force is higher than the surface tension force provided by the material. So what we need to do? In that case, we need to provide some support mechanism, which has to be removed later on. So we provide this support in such a way that the droplet can sustain like this, so that we can realize the overhang feature. This has to be done in the beginning itself. Okay. Once we do all this pre-processing, then we go for the build part, and there are 7 ways of adding material that I'll discuss briefly, defined by ASTM. Once we add the material, then we need to do some post-processing like this support, which we generated. We have to break this because it is not the final part of the final component, and then we need to do sometimes some finishing also, because what we build by additive manufacturing is in a layer by layer manner, and hence we get some staircase effect like this, and this has to be removed later on. So for example, you want to build this part and the surface was actually like this, but what you will end up building, it will look something like this. So you need to remove the material from here, and hence you can, so that you can get this accurate surface. Okay, how it works you can see in this slide, in this video. So basic principle is going to be same for all the methods of adding material. Okay, but the method of fusing the layers will change. Okay, different materials will be used and all. So first we use the deposit the outer contour, then we fill the inside area. Okay, and each time we process the same way and build the part. Now you can appreciate, like I mentioned, that this process can be used to build the models without any cutter, tool or fixture specific to the geometry of the object. Now whatever the geometry is, what will change at max is the contour, shape and size, and we are not really going to bother about it. Okay, if there is a 6 mm diameter hole, then there will be a gap here of 6 mm diameter, or it will be a gap of 8 mm diameter. Nothing is going to be changed otherwise. That is why the process is completely automatic. There are no chances of collision also, because each time you are building the material and your head is above the build part. Okay. Whenever you go for selecting a material 3D printer, you should always consider 3 factors, like what is the material you are using in your 3D printer, what is the minimum layer height, because that is going to define your final quality of the object, and third is what is the support mechanism. because sometimes removal of support is very, very difficult in some processes, because, and particularly for metal, that is our today's focus also. So in the case of metal, having and removing support is a nightmare. So what we can do alternatively for that, we will discuss briefly about that also. Okay, so these three factors are most important when we are going to select any additive manufacturing process for your requirement: material, minimum layer thickness, and support mechanism. Based on ASTM, the additive manufacturing processes have been classified into 7 categories. First is wet photopolymerization. In wet photopolymerization, what happened? A bed of photopolymeric material is kept like this, like you are seeing in this image. It's a tank full of photopolymeric material. On the top surface of this photopolymeric material, wherever the UV light will fall, that portion will get cured, and hence you can see in the blue color here. Okay, this UV light is usually, in the case of this type of process, is approximately 40 watt only. Okay, here if wherever support is required, we have to generate the support also manually, I mean to say in the CAD model itself, and which will later on has to be removed manually. Next is material jetting. Material jetting is very much similar to like your 2D printer, where you inject the material on the sheet of paper. The only thing is you need to immediately cure it. What we use in 2D printer, hot rollers to make the ink solidified, and instead of solid like this, you can use the photopolymeric material as well. Then the process, one example is the object. In that case, the photopolymeric material will itself inject on the sheet of on the substrate. Maybe you can assume a plain sheet, and wherever this material will fall down in the form of droplets, if the UV light will pass over it, that portion will get cured. The benefit here is you have control over each and every nozzle, and hence you can deposit the material with different colors also, and colorful objects can be made. This is called as material jetting. Usually the power here required is more than 40 watt, because here we want the solidification as much rapidly than it was usually achieved in the wet photopolymerization based process. Okay, so power is slightly higher here. Then is the binder jetting. In the case of binder jetting, we usually spread a layer of powder. Okay, and on that powder from top, ink used to come. I will prefer to call this process as ink jetting instead of binder jetting. That ink may have binder or may not have binder. So for example, if I spread a powder layer of cement-like material, then in that case it will be aqueous ink. Aqueous means just like your water. That doesn't have binder, but wherever that ink will fall, that portion will get cured. But if, for example, I have sand particles, I spread a layer of sand, then in that case aqueous ink may not work. It should have the binder particles also along with it. Okay, but wherever the principle is same, wherever this aqueous ink or binder falls, that portion get binded together, and hence the object is formed. The loose powder here act as a support material and can be removed very easily. The removal of support is easiest in binder jetting. Next is material extrusion. In the case of material extrusion, this is the most exploited additive manufacturing process. You might have definitely seen it. What we do, we extrude the material through a tiny orifice. So for example, you are trying to extrude a plastic, usually we heat it before extruding it from the tiny orifice. Why tiny orifice? Because we want the precision of the deposition so that you can build the part with very high accuracy. Sometimes people also use material like slurry, like in the case of construction industry, they mix the cement-like material with something, and then they make a slurry that get extruded through the tiny nozzle. That in that case, you do not really need the heaters. Okay. That is called as material extrusion in general. Next is sheet lamination. In the case of sheet lamination, the raw material is in the form of sheets. But please note, whatever way you are joining these sheets together, if you will not use a cutting operation, you will end up in making with the cube-like or cuboid materials always. So I mean to say, you are joining the sheets together, and the final object may always look something like this. You will have always cube or cuboid. So what usually in sheet lamination process, there is a additional thing is the cutting operation. So you join the sheet together and cut the periphery, which is your main part bounded inside. Then the remaining portion you cut in such a way that this portion can be removed later on, and hence you will have the final part inside buried. Okay. Now if it is paper sheet, the sheets can be joined by thermally activated glue or normal glue, and if it is like plastic like material like your sellotape, there also the glue can work. But if it is sheet like of metal, because that is our focus today also, then you need to use the processes like ultrasonic consolidation or friction stir welding, the processes where sheets can be joined together. Okay, next is powder bed fusion. In the case of powder bed fusion, we use this spread a layer of powder, and from top a laser used to write. Laser, or it can be electron beam as well. Some means of energy we throw on the powder bed. Wherever this energy beam falls, that portion get melted and fused with the previous layer or substrate, and hence we build the part in the Z direction. Next is directed energy deposition. In the case of directed energy deposition, we use arc, laser or electron beam in such a way that it creates a molten pool on the substrate, and in that molten pool you either inject powder, strip or wire, any form of raw stock material, but the molten pool has to be created in the substrate. Usually the power utilized here is in the range of 6 kilowatt, up to 6 kilowatt people used to use. While in the case of powder bed fusion, the usual power is 600 watt. In IIT Guwahati, soon we are going to have a big a powder bed based 3D printer, which will have 600 watt laser power. So now you can see why additive manufacturing, the ASTM has aligned these processes like this, because this is based on the energy consumption. Why I was talking about the wet photopolymerization in the beginning, because it utilizes only 40 watts. While I talked about directed energy deposition in the end, because it uses 6 kilowatt. And this hierarchy from left to right is based on the energy consumption required in the material. Okay. So like I said, the wet photopolymerization requires low energy, while the DD requires the highest energy, and this left to right, like photopolymerization, material jetting, binder jetting, material extrusion, sheet lamination, powder bed fusion, and directed energy are in the order of increasing the energy consumption. Now, this classification is good, but if I really want to discuss about metal, it will be difficult to utilize this classification. So I'll just rebuild this classification based on the raw material used. For example, the raw material in 3D printing can be in the form of liquid, or it can be in the form of solid as well, or it can be in the form of gas. However, there is no 3D printing process till now available which utilizes gas as a raw material. So let us focus on these two, liquid and solid. If it is liquid, it can be wet photopolymerization or rapid freezing, like your water-like material. When it falls on the substrate which is at very low temperature, it will immediately get freeze. So freezing type of processes where we print ice by water. However, metals really do not fall into this category, because we really do not use liquid form of raw material, because normally at NTP the metals are, we know that, at solid state. Now if we talk about solid, what are the different forms available? It can be in the form of sheet, powder or wire. When it is sheet, the example is loam, laminated object manufacturing, ultrasonic consolidation, UC, friction stir welding based process and all. Or it can be in the form of powder like 3D printing, SLS and DED, or it can be in the form of wire like FDM and wire arc additive manufacturing. This area here, really the additive manufacturing falls into this. Yes, because metals can really be converted into sheet, powder and wire very, very easily. So what is the scope today? Sheet we are not going to discuss, because it will take a lot of time otherwise. If you really are interested, ultrasonic consolidation is the commercially available process for metal additive manufacturing. Binder bed, now I'll come to the powder. Sheet is fine, and laminated object manufacturing also will not discuss. And what basically happened in this process, we used to have the sheets and we join them like we do in the transformer. In the transformer, we used to have sheets, right? You take the cutout sheets, just bolt them from the sides. Okay, this was the process developed in Japan long back. You just search about it, like called laminated manufacturing, and the cavities are created because the sheets are cut out. They just join together. You can even use brazing also to join the sheets together, and then the cavity can be used as a punching and the what you call punch and cavity for injection molding. Other than that, if the powder is the raw stock material, then there are two processes. Either it is powder bed. Powder bed means you spread a layer of powder, then powder doesn't move. Then from top, either binder comes or laser comes. If it is binder, then it is also available for metal, but we are not going to discuss that. So briefly, I'll tell about that here itself. When the binder comes from the top, it binds the metal particles or metal powder particles together. Now in the green state, that part lifted up and put it into the furnace. and hence the binder leaves the cavity behind into your green part. Now that cavity is usually filled by a process called copper impregmentation. Okay, and these cavities are now the part is now approximately 100% dense. The process, if you really want to see an example, is X1. X1 is a company which still uses the binder based process for making the metal parts. But here you can see the limitation. Whatever the material is, always the binder particles will be binded by the copper only, because the copper is the only thing which is holding these powder particles together. So we are not also going to discuss about this process also today. Other than that, if energy beam is using in the powder bed technology, that is something we will discuss. Okay, or if it is the powder is not pre-placed like this, we are feeding the powder, or sometimes also called a DD, direct energy deposition, also we will discuss in detail. Other than that, we will discuss the wire-based metal additive manufacturing also. In that, we shall discuss about two processes: arc-based process and energy-based process, energy beam-based process. Arc-based process like TIG, MIG, and plasma, and energy beam processes like electron beam and laser beam. So these are the processes we are going to discuss. So the scope of today's lecture is energy beam-based powder bed additive manufacturing, powder feed-based additive manufacturing, wire arc additive manufacturing, wire beam additive manufacturing, and in the end, if time permits, we shall discuss about hybrid processes and multiple technologies, where all these multiple processes are clubbed together to build the metallic parts. Okay, so first is powder bedding. In powder bedding, like I said, we spread a layer of powder, and then from top a laser comes. Wherever the laser deflects, that portion of the powder gets melted and fused with the previous substrate or the previous layer. Okay, this is how it looks like. After building, the part is ready along with the support structure. This is support structure, and then later on the support is removed. Basic principle is very simple, like I just have shown you in the video. In the energy beam based powder bed additive manufacturing process, an energy beam such as laser beam or electron beam is used for primarily or partially, I mean partially or fully melting the powder particles in the particular region of a layer to form fusion bonding with the pre-built layer. If a laser beam is used for partially melting or sintering the powder particles, then it is called as selective laser sintering. If the laser beam is used for completely melting the powder particles, then it is called as selective laser melting. Nowadays, SLM is more popular and slowly SLS is getting obsolete. What is the working principle? Can be seen from this diagram. There are usually two platforms. One goes upward, another platform goes downward. This is also called as bottom feeding mechanism. There are some top feeding mechanisms also. Okay, what it does basically, it goes above with the required layer thickness. So for example, the 40 micron is the layer thickness, then this platform will go above by 40 micron. As it will go above for 40 micron, a recoater will come and take away the excess material and spread over the another platform which is going down by the required layer thickness after completion of each layer. That is around 40 micron, like I said. It will fill this gap and hence a new layer of powder will be spread. Now from top, a laser beam will come and it will get deflected by a galvanometer system. In the case of electron beam, it is deflected by the electromagnetic coils. This laser beam get deflect and falls on the bed like this. Now when we build the part, usually the droplets are supported by the loose powder. No issues. The droplet will not go down. But what happened? The part may deflect. To avoid that deflection, we use support. I'll come to this point why we really need support mechanism in powder bed technology. Although it looks like the droplet will not go down, why do we really need support? On the machine system side, let me discuss briefly today about the beam deflection systems which we use in the powder bed technology. Also, we shall discuss why we really need support structure. Also, let us discuss about powder recoating system, different types of recoating systems. Briefly, very briefly, I'll discuss about that. And the fusion mechanism in the end, where we shall define what is SLS and SLM. So basically, the beam deflecting system looks something like this. This is the schematic diagram of the same. So what I have shown here is that there is a motor. This motor is corresponding to the x-axis and this motor is corresponding to the y-axis. On these motors, two mirrors are mounted. One this you can see in the blue color, another in the green color. As the motor can rotate these mirrors with a very high speed, the scanning speed can also be very high. Okay, so what is happening basically, this red color laser beam falls on this blue mirror and then it falls onto the green mirror, and hence it falls downward like here at point A at the center. If for example the mirror corresponding to the x-axis rotates from blue to pink color, it get rotated by an angle dx, then what will happen? The beam will not deflect at this point. Instead, it will deflect at another point here, and hence the beam will move in x direction. So the motion of this mirror is moving the beam in x direction, correct? Now there is another mirror, like I said, if that moves, the motion will be corresponding to y-axis. So if this beam is falling like this in the pink color and it is projecting on this brown color, green color link, then it will definitely fall down like this. But if this mirror corresponding to y-axis also rotates by an angle theta y, then you can see its new position is this brown color link. And hence what will happen? The beam will be deflected away in y direction. Hence you will get the motion in y direction. Appropriate motion or appropriate rotation of this galvanometer corresponding to x-axis and y-axis can move your mirror, can move your laser beam on the powder bed along with x and y direction. Okay, so it can move in x direction and y direction appropriate. So very easy to write a code for that. You can easily write in MATLAB, and you can generate the corresponding you can generate a relationship between the xy coordinate on the bed and the theta x and theta y corresponding to the galvanometer. So this system of mirror is called as galvanometer. It is not really very difficult to understand, okay, with the system, but they call it as galvanometer, which consists of two perpendicular mirrors mounted on the two motors. There is a issue. When the galvanometer deflects the mirror away, beam away, let me just clean this slide, then I'll come back. Yeah, when the laser beam deflects the beam away from the center, what may happen? You can see at the center it will remain a perfect circle, but if deflect away, then the cross section of the beam will become elliptical, right? Because you are just cutting a tilted pipe, for example, by a horizontal plane. And if you cut a tilted pipe by a horizontal plane, we know that the cross section will be nothing but the ellipse. Hence, what will happen? The power density will change, because if your power is constant for the laser, for example, 600 watt, its area is changing here. Here the area is pi a square, while here the area is pi ab, where b is greater than a. Hence, the power density will change. It's obvious. What to do? Ideally, what is the ideal condition? That if the galvanometer is rotating, its focal point will remain circular in this trajectory, what you're seeing in blue color. That is a spherical trajectory. In spherical, but we do not have a spherical chamber. You know that you have a flat bed. If you will be able to spread your powder on this spherical thing, then no issues. Then you can really make the part. You can just spread the powder particle on a spherical platform, and then there will be no issues. But really, that we do not do conventionally. So what we do in that case, we have to use some correction methods. There is something called f theta lens. So what is happening here? Right now, the focal length is this, that is equal to r, because usually the focal length of the mirror of a lens is constant. Okay, I want to change the f if the angle of projection is changing, right? So what I need is a f theta lens. F theta means correction in focal length when the beam is incidenting at different value of theta. So this lens is a function of f and theta. The focal length changes when the beam falls on the lens at an angle theta. Okay, this is called f theta lens, and it corrects the beam focal length in such a way that you get a circle on the bottom side of the bed. But the issue is you can't really have a very big f theta lens, and there are issues with the heat also involved with the laser beam, and hence that is why all the 3D printing machines are limited to the size 300 by 300 by 300. So today, at least I'm sure now you know the reason why this powder bed technologies or powder bed machines are limited to this size of 300 by 300. There are machines beyond this, but then they have to use multiple lasers. Single laser best can scan in 300 by 300. Okay. Now next is working principle of recoating system. Okay, like I've already mentioned, most popular one is the bottom feeding. In the laser based system, mostly you will find this bottom feeding system. In bottom feeding system, you have two platforms. This one is going up above and this one is going downward. Usually they have additional platform also to increase the productivity. How it works, let me explain to you quickly. This platform goes up, the excess powder is taken away by the roller or doctor blade, silicone blade or brushes, and this powder is spreaded on this platform, second platform, which goes down by the desired layer thickness. And this roller be stationary and the excess material just fall onto this this collector. Then after scanning, the roller is here, it can again go back. So in both the stroke, while going backward and forward, the roller will spread the material on the border bed, and hence the cycle time can be reduced. Because you see, the scanning of layer is not a very, it really doesn't take much time, because the speed of laser is around 10 meters per second. It's very fast. While recoating takes time. So we need to make a process really faster, so that way you can really spread the layer in a faster manner. Okay, now this is the top feeding, typical setup for top feeding. Usually electron beam uses this method, EBM process. In that, the hoppers are kept on the top. What you are eliminating, you see that here you need to use two motors, right, to feed the powder. Here they are utilizing gravity. Okay, two motors are completely eliminated. So utilizing the gravity, powder is falling down. Hence, you can utilize the feeding of powder here under the gravity, and hence it can be spreaded over the powder bed. The recoaters can be of three types usually. Either it can be a straight blade like this, it can be of ceramic, metal or silicone. Why silicone? Because silicone is usually a flexible material, and if there is a warpage in the layer, it can accommodate. While the accuracy of deposited layer may not be very good. To get a very good accuracy, you should use a ceramic blade. But the ceramic blades are brittle in nature, and hence if there is any overhang and if it strike with the ceramic blade, it may get broken, and the inclusions may be there in your final part, which may not be really desirable in many cases. Okay. Now other case where when we use the powder like non-metallic powder like plastic and all, in that case we usually prefer the counter rotating rollers. Why? Because in that case we need to give some densification also. And this counter rotating blade rolls as well as it compacts the powder locally and spreads the layer. The third one is top feeding like this. In that case, the hopper based feeding in like this, in which there is a gap between the hopper and this platform going down. Each time when the gap is not there, powder will not come. When the gap will be there, the powder will fall. This is not really a very accurate method. So accuracy is coming from left to right. The most accurate is this one. So accuracy means coming from right to left. So most accurate is spreading the layer by the recoater or doctor blade. Now why really we need support? So for example, you are going to build this overhanging feature. Fine. And you are depositing material here. The loose powder is already available. That will not allow this molted material to go down. Okay, so that is not the issue. When you talk about, for example, welding based process, and you are trying to build this part by welding based process. So what will happen? In that case, the material is coming from top, right? And there is nothing available here. Nothing available in the case of powder bed, in the wire based processes like a welding based process. In that case, the droplet will fall down. But here you have loose powder. Then why we really need this support mechanism? The loose powder is already there. Okay, so we really don't need the support material to support this overhang feature to go downward. We need it to not allow it to go upward actually. Okay, so if you have a material, for example, which is having very less value of alpha, alpha is nothing but thermal expansion, alpha delta T. Okay, so this alpha, if the value of alpha is less, then it will not deflect much. But if alpha, which is usually high in the case of metal may deflect. What will happen? I'll just try to show you. You can build the part till this portion, no issues. Then after that, laser beam will scan over it. It will look something like this. When the laser will scan, you can see it's a very thin layer. It's of 40 micron. What may happen? It may deflect like this. Okay, because there is nothing to hold it from the bottom. And the L by D ratio is very less. The layer thickness is very thin. It's 40 micron. And for example, this overhang is too large. It will not sustain. It will just deflect. But if the overhang is less, then it may not. That is why for a certain overhang, only we require the support mechanism. Beyond that, we really require support mechanism. Lesser than that, we really don't need support mechanism. As you can see in this diagram, this particular diagram, you just look at this. The support is required only for some portion, and this portion really no support was there because this is not a beyond a threshold value. If it is beyond a threshold value, then only it will deflect, and it depends on material to material. So very, very important parameter, that what should be the overhang angle, because that will dictate how complicated part you can make. Like if you are using non-metal and using laser for sintering, basically, in that case, no issues. You can build any size of the part. That is why most complicated parts you can build by laser based SLS for non-metallic parts. Okay, so to restrict this deflection, we use the support. Now I'm sure you might have understood. So, and this support should start from the bottom of the substrate. Okay, so that you can hold it properly, the deflection. Okay, now I'll come to the fusion mechanism. There are two ways of fusing the material together. The principle is very similar in the case of, now let me discuss about first the sintering. And the process in that case will be called as selective laser sintering. Please note that I am using laser as a heat source. So in sintering, the principle is very similar to powder metallurgy, but for the absence of compaction. The green part is prepared on the machine after partially sintering, and sintering is complete inside the another furnace later on. When a laser beam scans on the selected region or over a layer of powder, the particles in that region got fused together. The remaining particle as a support material in this case. Please note that. Because you are sintering, you really do not need support mechanism. You are not completely melting because your delta T is very less in that case. And you are just fusing the outer periphery, I mean. You are not completely melting the powder. As the delta T is less, you will get less thermal distortion and hence less distortion, of course. So laser beam is positioned along a small mirror using a small mirror capable of deflecting the in two direction. What we call it? We call it as galvanometer. The powder of the laser decides the layer thickness, the power of the laser. If the layer power is high, of course, we can go for higher thickness. Although, in that case, we need to make a compromisation with the surface finish. Explicit support structures are not required. Like I already mentioned, in that case, the powder particles do not really melt. Okay, if the melting is not happening, the deflection will not occur because the delta T value is less. A wide variety of powder can be used. There are two types of selective laser sintering processes. One is called as indirect SLS. Another one is called as direct SLS. So let us see what is indirect SLS first. So in the case of indirect SLS, it can be basically applied to any material that exhibits a lower viscosity upon heating. For example, thermoplastics. Thermoplastics satisfy this requirement. They also can be rapidly heated to soften or melt and cool to solidify as the temperature passes through the glass transition temperature, that is called as TG, and sometimes the melting temperature. So for example, you have ceramic particles. These are the ceramic particles, and or maybe metal particles. They are coated with some thermoplastic polymers, and it is used as a fugitive binders in the powder. The idea is to have a low melting point material somehow adjacent to the powder substrate. These are the powder substrate, powder particles. Around that, the idea is to have somehow the low melting point fugitive particles. Later on, I'm going to delete them. So what we can do, we can just produce, when the laser beam will write, the laser power will be very less. In that case, only these thermoplastics will melt, or they will pass through that glass transition temperature and they will get fused together. No melting will happen between the ceramic, obviously that will require very high temperature, and the metal also. We prepare the green part in that case. Okay. After that, we take this part, which is basically binded together only by the thermoplastics. We take it to the furnace and eliminate this binder. It will leave the cavity behind. Hence, further when we eliminate the binder, you need to, as the density is going to reduce in this case, you have to use some implementation technology where we can use like copper implementation and all, which can take this place of this cavity left behind the elimination of the binder. Okay, so like I said, it is written here, when the binder eliminates, route is taken, the part can be sintered to fully dense, or the voids left can be infiltrated with the suitable material. Okay, the green part we produce by this machine have usually lower density. Okay, but the parts produced by this are nearly isotropic. The strength is same in all the direction, although less, but same. They are free from any internal stresses because we are not really melting the metal particles in this case. While the first later two features are desirable, we need isotropic, free from internal stresses, but the last one, lower density, is not a desirable process. But remember that no explicit support mechanism is required when you are just sintering. So for example, if there is no metal, only or everywhere is thermoplastic, you can see no support mechanism will be required. Other than that, let us now discuss about direct sintering. In the case of direct sintering, mixed powders enables this particular process without the use of polymer binder or a special developed metal powder, which we had discussed earlier. The first direct metal sintering process machine was developed in 1995 by EOS. Okay, they uses 200-watt infrared laser with a spot size of approximately 100 micrometer. The system uses a pre-alloyed powder. Okay, the powder looks something like this. It is pre-alloyed. Fine. It yields a laser cure width of about 600 micron at a scan speed of 3 meters per second with a standardized layer thickness of approximately 50 micron. Okay, so what happened in this case? You cannot use any other material. Only the pre-alloyed metal on the surface can be used. Now this pre-alloyed thing can get melted at lower temperature, and that will only fuse with the previous other particles. The main material, the main center metal will not get melted. And hence this is also a sintering process. You are not really melting the center particle, and hence the support will not be required. Other than that, what you can do, the material to be sintered comprise a structure powder with a high melting point and a binder particle with the low melting point, so as to promote liquid phase sintering, something called as LPS. For instance, let us assume the sintering of nickel and tin. Nickel melts at 1455 degrees centigrade, right? While tin melts at 222 degrees centigrade. Now, if I have a mixture of these two particles like nickel and tin, and when laser is writing over it, what we will have in the end, because tin melts and it will make a reaction with the nickel, of course, and it will make a compound called Ni2SN. Fine. And hence you will be able to bind the nickel part, this particular component. Now, definitely the melting point will be something else. It's an alloy, but you have made here. But it is very, very limited to some particular materials only. But it is possible to use two different materials, two different particles, where the one with lower temperature or melting point, another with higher temperature melting point, and make sure that they make alloys. Fine. So this was the sintering. Now let us discuss about melting. Nowadays, this is more popular. In this case, we have to prepare the CAD model along with the slicing mechanism. And the slicing is usually defined with the overhang feature, and which depends on the material to material. The working volume is maintained with appropriate temperature so that the laser supplies the energy just required to cross the threshold value to the sintering temperature. The inert environment is created using continuous supply of gas like nitrogen, argon, or helium. Most preferable is argon. However, the cheapest is the nitrogen. It is to minimize fire hazards as the fine particles have high activations. Each slice or layer is realized using the following step. The table lowers down by the layer thickness and a layer of powder is spreaded. A beam scans the layer of powder, thus the required region is selectively melted. After all layers are made, the table rises completely, leveling the block of cake with the part inside. The surrounding powder is soft, which is removed easily by the brushes. However, the support created has to be removed by process like grinding or wire cut EDM. In this particular case, this part I have cut because we do not require the copper implementation. We directly get the fully dense part in this case. While in the previous case, we really do not get the fully dense part. However, we saw that direct sintering can give you the fully dense part, but in that case, the material was very limited. It cannot be generalized. Now, as selective laser melting come into the picture, any material can be used theoretically. And if you remember why we do not use the any material earlier, because OEMs were limited. They were not allowing us to use any material because you can't really melt it and form the actual part. Nowadays they are allowing us to use any material because they are using the principle of selective resin melting. The major players in the market are written here like SLM, DMG Mori, Renishaw, Sysma, EOS, and 3D Systems. Now I shall discuss briefly about the electron beam melting. In the case of electron beam melting, we use electron beam instead of laser. This is the video by Archem. Here, like I have explained, they uses the top feeding mechanism. The principle remains same. They start with the CAD model, do the slicing, and then they process with the machine. So this is the typical architecture of their machine. These are the hoppers, and they are on the top. That is why it is called top feeding. And both the hoppers used to have the material, so that the blade, when it goes left to right or right to left, it can spread the material and the productivity can be improved. So when the blade is going left to right, it is spreading the material, and first the preheating was done by the electron beam. Then the main material was melted. Why preheating is done? So that when it gets melted, only a certain amount of delta T can be given, and hence the stresses will be least in this case. As the whole thing is happening inside the vacuum, the heat transfer is also very bad in that case, which we can utilize in such a way that we can produce the parts without the support structure, usually in the case of electron beam, because we maintain the temperature just below the melting point, and in the local region only we just improve the temperature from the maintained temperature to the melted point. And this change is so less that your stresses generated will be only alpha delta T, and delta T, like I said, will be very small. The deflection will not be much, and hence the loose powder itself will be able to hold the part. It will not allow it to lift up. Okay, this freedom is not there in laser based systems because we don't really use the we use organ and other things, and only the temperature can be maintained from the bottom. But I remember nowadays 3D system has started developing a system in vacuum, and I'm sure if the vacuum is used, you will be able to use maybe preheat the powder in some manner with a high scanning speed with the laser maybe, and or by utilizing multiple lasers inside, so that the powder bed can be maintained at a particular temperature, and the entire chamber can be maintained at a particular temperature which is just lower than the melting point of the powder particle, and hence you will be able to eliminate the residual stresses and can produce the part without the support structure. Now let us discuss briefly about the powder feed AM. The powder feed AM typical system looks something like this, as you are seeing in this diagram. In this video, you can see from the center laser used to come. It creates a molten pool on the substrate. In that molten pool, we feed the powder. Wherever, when the powder particles fall or strike with the molten pool created by the laser or electron beam, or in the case of electron beam, we usually use wire, we can't use powder. That portion, portion, the wire or powder or raw stock get melted and fused with the previous layer. It keeps on depositing the material and build the powder, build the part. Here you can see one thing: we do not have any support, not even to support the droplets to fall down. No support mechanism is there at all. So we have to come up with something which can be utilized to create the overhanging features. We shall discuss how people are doing. Typically, a powder feed based additive manufacturing system looks something like this. Okay, it is also sometimes called a DED. So I'll interchangeably may use the name DED for powder feed based additive manufacturing systems. It usually consists of a powder feeding unit. Powder feeding unit usually consists of powder feedstock metering system. Metering system means it measures the right amount of powder. Then powder conveyance system, which convey the powder towards the powder delivery nozzle. Okay, so here you can see this is the metering unit. It measures the right amount of powder, gives it to the distributor where it can mix the different powder particles, and appropriately it conveyed from distributor to the delivery nozzle. Okay, how usually the powder is distributed? It distributed with the help of powder conveying gases like argon. So argon used to go there, it takes away the powder from here, and then it just takes this powder towards the powder delivery nozzle. And then these powder particles are delivered to the molten pool, carried by the organ gas. There is a laser system in the center. That laser is focused on the substrate. It creates a molten pool, and in that molten pool, we feed the powder. Now there has to be synchronized motion between the molten pool created by the laser, because in that only we are depositing the material. As the powder substrate, if the substrate has a synchronized motion between the powder delivery nozzle, we will be able to trace any trajectory, and hence we can deposit the material along with any curve. The subcomponents basically for powder feeding unit are shown here. There could be many ways of measuring the right amount of powder. Like you can measure the powder by using the dispensing method, screw method, feeder wheeler, or electrostatic. Or you can also convey the powder from one end to another end utilizing the mechanical method like vibration, screw, or gravity tubes. Or you can use the pneumatic methods to carry these powders along with the organ. The delivery of powder towards the molten pool can be done by three ways. It can be gas assisted, like the same organ gas can deliver the powder, or you have to use some vibration or gravity driven feeders are also nowadays available. We at IIT Guwahati are also trying to develop a gravity driven system which can deliver the powder towards the molten pool utilizing the gravity. The benefits are few, like in the case of electron beam, where the vacuum chamber is there, we cannot deliver the powder particles along with the organ, because otherwise the vacuum will be lost. Hence, a gravity driven system is somewhat important nowadays. Also, we have seen the involvement of organ when it is going towards the molten pool creates some issues like high velocity of powder, the powder particles bounce off, the porosities and all. So we thought of developing a system which can generate, where the powder can be fitted nicely along with the gravity, and the velocity of the powder particle can be given through some mechanical means. Like I said, powder feed based systems are popularly known by directed laser deposition, laser consolidation, laser engineering net shaping, direct metal deposition, direct laser deposition, and 3D laser cladding. If you want to know more about this powder delivery systems for powder feed based additive manufacturing, you can refer to my recent journal published in Additive Manufacturing Journal. There are different ways, like I said, particularly for powder delivery nozzle. The first, which was developed by William Steen in 1988, looks something like this, where we used to have a CO2 laser at the center. This CO2 laser is not visible because it doesn't fall into the wavelength of visible laser, and then it creates a molten pool here. In that, from side tube, powder is deposited. This powder is carried by the organ gas, and these particles falls into the molten pool created by this. This was the very simple system and the very first one developed in 1988. Later on, lot of systems came into the picture, like definitely this type of system is called as off axis. You are depositing the material off axis to the center part. While we really do not desire it nowadays for additive manufacturing because of something called as omnidirectional. However, omnidirectionality is not the scope of today's lecture, but just briefly I'll tell you, in that case, we should keep the feeding mechanism consistent throughout the process. So for example, if we are always doing front feeding, we should maintain the front feeding. If we are feeding the powder from back feeding, we should always maintain the back feeding. One particular kind of feeding mechanism should be maintained. While in the case of off-axis deposition, for example, you are feeding the powder in this direction and moving in any direction of the substrate. For example, you are moving left to right, it will be back feeding. And if you are moving right to left, it will become front feeding, right? So this may not be really desirable, and hence in off-axis systems are not really popular for powder feed-based AMs. Other than that, nowadays continuous coaxial systems, like where the powder is coming in the form of a cone and center is the laser, you can utilize it in such a way that now you move in any direction, the process will be consistent. The direction of the feeding will remain consistent. Or you can use discrete coaxial, where multiple nozzles can be used to feed the powder, and hence the process will be approximately omnidirectional. Other than that, the recent one is the central feed, which I have found developed by in the literature in some Chinese paper, where I have seen the laser is at the center and the powder feeding is done in the form of a cone around it. Okay, so this type of systems are nowadays available for powder delivery nozzle. What are the popular systems? One is for this particular powder feed AM, DMG Mori. Optomac. Optomac is the oldest. Their system is called as lens. Then form alloy, coherent or OR laser, Instack or beam. Just typically, I just want to show you that what kind of power they use. The power here in the particular model is approximately 2.5 kilowatt to 3 kilowatt. They utilizes a fiber diode laser with a beam spot diameter of approximately 1.2 to 2.6 mm. Okay, the laser head is integrated to the headstock and we can easily change it like an ATC in the automatic tool changer in their machine. They uses continuous coaxial nozzle. Continuous coaxial nozzle, this one they prefer to use. And the build rate is approximately 2 kg per hour. The inert gas they use is argon, and the particle size for injecting into the molten material is approximately 45 micron to 125 micron. They uses a 5-axis deposition system. Now this is something which is used to eliminate the support mechanism. I'll just briefly talk about it. And their working volume is quite big. They can go up to 2.6 meter by 3.8 meter by 2.9. Very, very big machine. Optional model for including the additive and subtractive manufacturing together is also available. So you can use the milling process as well as the cutting deposition process together, and the process may be called as hybrid. What is 5-axis deposition? Let me just briefly tell you here itself. So for example, I want to build this part which is having an overhanging feature, okay, like this, and it is mounted on the substrate over here. Now from the top you are using a welding gun. Now you can see if I'm depositing at this particular location, what may happen, the droplet will fall down because there is nothing to support over it. So what I can do, I can tilt this thing. So if I have a rotary axis, I can tilt this part like this. And if I can tilt the part will become like this, correct? I mean to say something like this. Now in that case, you can support it from the vertical like this. And hence the droplet can fall down nicely over it. There will be no droplets which will fall away now. So for that part, you have to use a proper process planning, and hence it is called as and it may require multi-axes like 5-axes. Okay. Other than that, I have found very interesting paper in 2000 published by Slinger. What he did in the powder bed fusion. However, I have not found many other study on that. But why not? It looks very innovative. What he do, for example, he wants to make a closed overhang feature like on a box. So he can build the part up to here without any issue. There is no overhang here. Then what he do? He just switch off the laser. While switching off the laser, he fill the inside part in the boundary by just the loose powder. Then after that, for scanning the top layer, he just switch off the powder. Now only laser is on, and he basically do sintering. So it becomes like powder bed now, and hence the top layer get cured. He basically does the sintering. Then after that, he do the melting and build the part. Like this, he just demonstrated this type of cross sections. You see that it's a rectangular cross section which is hollow. Although I can understand that the entire powder may not, the surface finish you get here will be very, very bad, because anyway you are sintering the material and the powder may be stick to it. However, but this process can be explored further. Other than that, what you can do, like I have explained, you can tilt the part utilizing the multi-axis kinematics. Okay, this is what we are doing. Even I am doing here. So for example, the MIG welding gun is like this, and it is depositing the material on the edge of it. As the material is depositing on the edge, the droplet may fall down. You can appreciate this need immediately. Hence, what we need to do, we need to tilt the part. Now you can appreciate that the part is tilted, and hence the deposited material will not fall down. It is aligned appropriately. So usually we need to have a tangential normal over it. So extensive CAPP is required for that. We do extensive research in that area also, and we utilize some professional CAP package and develop our own also, where we can identify when to tilt the part, how to tilt the part. Okay, this video will show you how this process, this tilting works in the physical environment, and how does it look like. When there is no overhanging feature, you can see the deposition will keep on happening in a appropriate conventional manner. Okay, so it is depositing the material in 3 axes only. When overhang feature will come, the machine will tilt. You can see that. So let me just fast forward it. As there is no overhang feature, now it is about to come. There will be an overhanging feature in this direction soon, and you will see the machine will tilt. You see that. As the machine is getting tilted, now the droplets are falling appropriately along with it. So based on the requirement, the machine will keep on tilting itself and the material will get deposited appropriately to utilize the overhanging features. Fine. So this is about the tilting of the part. Now, even though when we build the part, to realize some feature, you need to tilt them, like for depositing the plates. A very similar component I have built in 2014. I'll show the video also of the same by utilizing the wire arc additive manufacturing. So like this, you can build the part. And then after that, on the same machine, you can finish it as well. Other than that, the powder feed based AM processes can be used for laser cladding, for cladding a layer over the surface of the pre-built part, or you can use it for repair purpose as well. In the repair purpose means when you have a part which is got burned out at a particular location, you can add the material locally on this. Okay, when a material is added locally on that, the part get repaired. And it is the flexibility only we have with DED based systems, while with the powder based systems, this type of flexibilities may not be there. You cannot repair the part locally in the case of DED basis, in the powder bed based systems. Now, if you have any doubt, let me know. Otherwise, I'll discuss now about the wire additive manufacturing.
So, dear participants, if you have any doubt, then you can write in the chat box, or you can unmute yourself.
What is wire additive manufacturing? Basically, I'll start with its history. Okay, in 1920, the process was already invented, where they used to use the MIG welding process to deposit the material. Okay, so they call it as a method of making decorative articles. In that case, these are the parts, and you deposit the material locally in such a way that you can build the decorative articles. The process is not really new. It was long back invented in 1920. Like I said, DED based process or this type of processes can be used for repair purpose. In 1930, I have found a patent in which the brake drums are repaired by locally depositing the material. Okay, and as the local material is deposited, the parts can be repaired. So repairing was invented in 1930 by using this process. In 1957, I have found a patent in which the electron beam, like in vacuum chamber, the material is deposited by using the wire, very similar to your vacuum based system. Okay, in that case, now electron beam is still not very stabilized, but the patent we can see was very long, was filed long back in 1957. Other than that, in 1966, I have found the patent in which they proposed to build a very long structure by utilizing the wire arc additive manufacturing. You can see here big vessels. Multiple wires were invented in 1972, where multiple wires can be used. However, they used to use these wires for welding definitely, and to increase the productivity. But now you can imagine that if each wire is of different material, maybe RGB, I'll say, in red, green, and blue color, and you control them appropriately from outside controller, and the feed rate of each wire will define the percentage of the material locally deposited in the molten pool. And hence, you can really make the functionally graded material. Like you can deposit really material as per your requirement, and you can make the on-the-spot alloys in this case. Fine. Or you can use the wire arc. I have found a patent in 1979 where laser was used along with the wire. So there is a laser coming at the center from the top, and it is creating a molten pool. In that molten pool, one can feed the wire. It gets melts and builds the part. The induction-based system was developed, which was invented in 1980. I have found a patent in which the wire is fed and it gets heated up by the induction heating. Later on, air supplied or the organ is supplied from the bottom. That organ takes the powder particle, the molten material particles towards the substrate and inject appropriately. And the injection of powder particles on the substrate will keep on happening, and you build the part appropriately. In 1992, Professor Dicken, PM Dicken, Prince Dicken, he has developed a rapid prototyping process, and really in 1902 he was able to realize all these patents. I have not seen any physical object, while in the case of while in 1979 by Professor Dicken, I have seen that the actual parts were really made. Okay, so you can see that these are the parts actually made by the process, by the MIG welding based process. Okay. Now I'll just come to the wire arc additive manufacturing. Okay. What is arc? Here, if you use MIG welding, TIG welding, or plasma, then the process will be called as wire arc additive. Typical setup of wire arc manufacturing looks something like this. This one is for MIG welding gun. In the MIG welding process, there's a wire. This wire creates the arc between the substrate, because there is a potential difference provided between the substrate and the wire. Okay, and hence, for example, if I say that this is positive and this is negative terminal, more it will be generated on this positive terminal, and hence the wire will get melted and it will get deposited. Okay, instead of MIG welding, one can use TIG welding as well, or plasma also. So what you need, basically, you need a wire feeding unit which can generate the, or a heat source, like in the case of TIG welding, we need a tungsten which can create the heat, and a wire feeding unit into the molten pool. What else you need is a synchronized motion between the wire feed, heat source, and the substrate. Fine. Once you have it, then the setup is ready. As you can see, this is a 5-axis CNC machine setup I have developed in IIT Bombay, where the head, welding head, is mounted on the spindle of the machine, and on the spindle of the machine, wherever it moves, it will deposit the material appropriately. Fine. This is the wire arc additive manufacturing group of Cranfield University. They have recently built the largest part by VOM. You see the size of the part built by this process. They usually prefer to use robots. Okay, so they mount their welding guns, like I talk about MIG welding gun, on the robots, and then they deposit the material on a very long trajectory. So robots are good for achieving building the large part, while CNC machines are required, because anyway, while depositing the material by MIG welding, you will have a layer thickness of approximately 1 mm, not less than that. If it is such a large thickness, then you will have a very bad surface finish, because the layer height only defines the surface finish in your final part. Correct? If the layer thickness is less, the surface finish also be better. So you need definitely a finishing machining, finishing operation like milling in the end of building the part by VOM. So that is why we prefer to use CNC. But if you are using robots, then later on you need to take the part to the CNC machine, maybe to clean or to give the desired roughness. In 2018, Gaffertech, a company in Germany, they have launched this machine, and what they did, they basically used the similar concept, and they utilizes the MIG welding process on top of it, and they build the part. And they use a CNC machine instead of robots. Okay, they build the part by keep on depositing the material on the substrate. Okay, now, however, I would like to mention here that in 2014, we have already done this and built some parts using it. If the time permits, in the end, I'll show you the videos of that also. Now, this was about the MIG welding. Now, if you are using TIG welding or plasma, how the conventional process looks like, that you have a TIG welding and you are feeding wire from the side. Okay, there are issues. You can use CNC machine or robot, that is fine, but there are issues in the conventional system. What are those? So, for example, you are moving on a circle. Okay, let me just restart the video again. For example, you are moving on a circle. Right now, this is this side feeding. You are feeding wire from side. Now, it will become front feeding. Now, this is front feeding. Again, it will become side feeding. And again, it is going to become back feeding. So, back feeding, side feeding, front feeding, everything is occurring while depositing on the same trajectory. There are a lot of issues with that. We really can't afford it, because the result here is non-uniform width and bead height. You see that the bead height is got spoiled at that location, and it was something else at some other places. Also, not only this, the metallurgical properties also changes. The process doesn't remain omnidirectional. Like I said, recently, if you want to know more about this new term, which I'm saying again and again, omnidirectionality, you may refer to my recently published journal in ASEV. In that journal, we have defined a new terminology called omnidirectionality in additive manufacturing systems, and how it can be solved for all the processes, not only for wire like metal-based processes. Briefly, I'll just show you how it can be resolved. Like the issue was the feeding mechanism. So instead, if you rotate the work plane You can see all the time now the front feeding is maintained. Right? You see that it is rotating and all the time always front feeding, right? Or you can rotate the wire feeder. When you rotate the wire feeder, the setup will look something like this. We have already developed it long back. Now, when you are moving in a non-linear trajectory, each time the wire feeder will also rotate appropriately. And yes, it has to be properly synchronized with your controller. Fine. So if you are going to deal with TIG welding based process, you have to use these type of arrangements in future. Otherwise, you cannot sustain when you are going to deposit on the non-linear trajectories. Next is wire beam additive manufacturing. Beam means it can be laser beam or electron beam. Okay. The same issues will come in the case of laser also. Like in laser, you have a laser beam and you are feeding wire from here. Now, if you are moving on a non-linear trajectory, you may have side feeding, back feeding, and all these kind of feedings. So, we have flexibility in laser that you can actually play with the laser beam appropriately. There is a head developed by Precitech. This one, please look into this. What they did, they just split the laser beam in such a way that you get the donut shape of the laser beam at the bottom. When it is a donut shaped beam, you can insert the wire at the center. So what is happening? There is a solid beam here, laser beam. It is passing through the optics. First, it passed through the lens called axicon. When it passes through the axicon, it becomes donut shape like this. So from a solid beam, it becomes a donut shape beam. Then it passes through a prism, which splits this donut beam into two parts. As soon as it got split, one can feed the wire from here. And again, we deflect it and passes through it as a reverse prism. The laser beam got merged again together like you see here. Then again, there is a sphere or protecting window which converts this beam towards a particular focal point. And hence your wire is at the center. Now it is like a MIG welding. Wire is at the center and a conical shape of laser beam around it. This head is developed by Precitech. So if anyway in future you want to go for buying a system for laser beam additive manufacturing, I'll recommend you to check for such systems. So this particular head is by Precitech. A similar head was developed by Fraunhofer, where they used 3 beams instead of donut shaped beam. This head was procured by IIT Bombay 2-3 years back. And here what they do, they instead of using donut beam, they use 3 beams. The same laser beam is split into 3 parts, and then from 3 sides, like you see in the video, laser beam comes and wire comes in the center. Now there is no issue like side feeding, back feeding and all. You can move in any direction independently and the process is omnidirectional. Electron beam, there's a company called Siaki. They have developed this system where they use electron beam at the center and feed the wire from side. Okay, what they do, they rotate the substrate. Like you see here, the electron beam is coming from the top and feeding the wire from the side. Here also they maintain the front feeding or a particular type of feeding by appropriately rotating the substrate. Okay, in their case, they rotate the substrate. They are able to build very, very long part. You can see that in this case, they are going to make this circular part, and hence you see that the rotary table is there and this part is rotating. Observe that. And always front feeding is maintained. Okay. So this was about the laser beam manufacturing. Now I'll just briefly explain about the rapid manufacturing lab and the at Guwahati and Bombay, what we do here. So we have a process called hybrid layered manufacturing, which uses wire-based processes, and it is for metallic additive manufacturing. What to do? We start usually with a CAD model. You see on the right side diagram. Okay. Then we pass through this CAD model with the in-house developed software by me is called as Gati Nirman, and we just do the slicing and develop the tool path. Once we get the tool path, we start the process. First operation we do usually with the metal is the preheating, because many metals that really do not form bond, they do not really get fused if you do not do the preheating, like the hard material like P20 tool steel and all. We know that. Then first operation is preheating. After preheating, we go for cladding operation. Cladding here I'm saying, otherwise you can call it as welding also. We use laser, MIG or TIG, any one of them appropriately. Then after depositing a layer, we do face milling. So okay, let me just show you some diagrams also along with this. So we start with the CAD model, we do the slicing, we get the contours. Once we get the contours, and the tool path. Along with this tool path, we deposit the material by utilizing the cladding operation. Before that, like I said, we may do preheating also. This is how the deposited layer look like after deposit the material by MIG welding process. It may not be really very flat surface, so we keep on depositing for few layers, but then after that, as the oxide keep on floating on the top, they may even reduce the conductivity and the arc may become unstable also. So what we need to do in that case, we need to remove this oxide layer. So what we do face milling after few layers. This face milling will remove some 2-3% of the material from the top. That also carried away the oxide layers, and it will have, but you will have a neat surface available for the deposition of next layer. We do preheating if required and repeat the process. Okay, in between sometimes a hammering operation is also required. What happened when we deposit the material, lot of residual stresses get generated. We know that the tensile nature of the residual stress is not really preferable for us, and the compressive is preferable. So we do hammering operation. When we do a hammering operation, that converts the sign from tensile to compressive. Okay. Then we keep on depositing the material, and hence the near net shape can be obtained like you see here. This is the near net shape. Then this near net shape is further finished to get the final object. So this is the basic principle. By utilizing it, till now we have already explored 3-axis kinematics, 5-axis kinematics, CNC machines. We have already explored since last 7-8 years the cladding processes like MIG cladding, TIG cladding, laser cladding. We have already explored materials like aluminum, steels, tool steels. Also the in situ process like face milling, preheating, hammering have already been explored. In IIT Guwahati, also when I joined, immediately I have developed the setup you can see on the right side, and we were able to generate, deposit the part, and we were able to create parts here also in IIT Guwahati by utilizing the same process. Okay, it's a 3-axis machine, and soon in January I'm going to have a robot along with a 5-axis machine. Till now, by utilizing this system, I have developed these many case studies. I have already made a part ISRO, this part for this is a propeller built in IIT Bombay, and this part when I joined here, my student has built here in IIT Guwahati. Like I shown in 2014, not only the planar layer, we have already developed method called conformal slicing. So this green part is going to be built in a horizontal manner, as it doesn't have any overhang feature, on a 5-axis CNC machine. So right now we are retrofitting everything on the same machine, like MIG welding, TIG welding, laser welding, and the preheating, hammering, everything on the same CNC machine. That's why it is called as SSMA, single station multi-axis system. There are 5 axes involved here. Okay, so for depositing of center part, only 3 axes will be required. After depositing, you can see that the part looks something like this. Yeah, correct. Then after that, I need to build the overhanging feature that is in the red part shown here. And for that, I need to tilt the machine. You see that? This was done long back in 2014, like I said, and this process called SSMA, single station multi-axis, was completely explored. So you deposit the material, hence you have the near net shape like this. You can further finish mill it and get the final product. So this is the final product. We saved a lot of material, around 60% of material was saved in this particular case. Now we move to another level of it. Now this is my PhD. This machine I developed in, it is called as MSMA, multi-station multi-axis system. Here a 5-axis machine used to shuttle between the different workstations like MIG, TIG, laser, preheating, hammering, everything. And it will keep on moving between these stations to get the desired operation done. Now in IIT Guwahati, I am trying to develop this system on the right side based on robot, but integrated with the CNC machine. And we deposit the material on the table or the CNC machine by utilizing the robot. Robot will pick the different objects and perform the operation from the back side. And hence this CNC machine will do the machining operation when required. This will be called as robotic wire arc additive manufacturing or robotic WAM. This is the machine tool for micro HLM I have developed in IIT Guwahati immediately, and this case study was done based on it. In this case, this welding gun I use is a DC welding gun, very cheap welding gun. It cost me around 1.8 lakh only, and the entire setup not cost more than 15 to 20 lakh, and it's capable of handling the ferrous materials. The video I have already shown to you. Okay, so but once again, I'll just quickly show you the manufacturing of the impeller. So this is how the 3-axis BAM is currently working in IIT Guwahati. Deposit the layer, deposited the blades, and then build the final part. No spatter at all. With a very, if you appropriately control the process parameter and understand the process parameters, really you can build the parts very neatly. Other than that, in IIT Guwahati, I am trying to develop a multi-wire based system where in the TIG welding or plasma welding, I'll be able to feed not only one wire but multiple wires. When the multiple wires will be fed into the molten pool, you can create on the spot alloys, and the appropriate control of each and every wire will create the functionally graded materials, as you can see here. For example, I have RGB given to these 3 colors of wire, and I'm appropriately changing the composition, and I will be able to control the deposition of the part. So mostly, I do not really work in the side of material, and I'm not a material science scientist, and I'm not expert of that. But my job is to create this machine tool and to create the appropriate controller for that, so that the appropriate material can be deposited in such a way. We are also trying at IIT Guwahati to develop a friction stir based additive manufacturing process. Like I said, in the case of sheet based processes, a cutting operation is inherently required. So it will be integrated with the milling operation. We'll keep the sheet like this. We'll move the FSW tool along the path, and we'll remove the excess material from the periphery of it. And hence we'll be able to build the sheets in this manner. This approach will be called as paste and then cut approach. So first we are joining and then we are cutting it. Also, we extensively work in the CAPP, computer aided process planning. This is very soon you will find this paper online. It is under review. What we do here, we are developing some non-retractable tool paths. It is a single thread, so you can just pull it and it's a single thread. The issues with the additive manufacturing is whenever it got switched off and on, it creates some issues. So we do not really want to switch on and off. And also different type of turns, we may sometimes require more number of turns for some material, because a large number of turns or change in the direction of deposition quickly can lead or can give us the less residual stresses, while the long passes may not. But in some process we really prefer long passes. So such type of tool paths we are capable of developing now, and we call it as non-retractable tool path. The software is almost ready, and we will make it open source after a journal paper which is under review. Also, I am trying to develop a gravity-based powder handling system for directed energy deposition in IIT Guwahati. Like I said, that gravity-based systems are very much required for depositing the material in the vacuum. So this type of system is there. It is not only going to deposit the material, and we are getting a very good results on the simulation. A prototype is already built by my student, and it is also doing proper mixing. Multiple powders you can feed, they can mix on the spot just above, and you can deposit the material nicely on with a very confined focal point. There are different ways of achieving this. Other than this, also a review paper is, like I already mentioned, you can find in additive manufacturing journal to know more about it. So this is the prototype. First prototype we built, we experimented with using salt, and now recently the completely automated system was also built, and now we are ready to fabricate it. But we don't have a laser, and soon we are going to have a laser. Maybe in the month of February, the system will be ready at IIT Guwahati. Yes, I work in the process analysis also. We do thermomechanical analysis like element death and birth. You can see in Abacus. We do thermomechanical analysis. We do our tool path, whatever you have seen, the non-retractable tool path, how the arc will move over it, and how the thermal distribution will be there. If it is along like this, like a raster pass, you will have a very bad thermal gradient in that case. While it is moving in a very random manner, you see the thermal gradient is also not maintained in a particular direction, and the pathways will be different in different layers. Okay. Sometimes the FEM models are really time consuming. They take days to simulate a very simple problem. So we are also trying to develop some analytical models where I can build the part. I can actually analyze the parts utilizing the analytical models quickly and compare my different build strategies. On the powder feed based system side, also we are trying to simulate the powder feeding mechanism and trying to develop a powder feeding mechanism for spreading the layer appropriately on the powder bed. Okay, so this work is still under a very preliminary stage. We just started it a few months before, and the objective here is to develop a non-contact layer, non-contact based powder delivery arrangement. Very new to this area but I am trying to develop a micro additive manufacturing system where I'll use electrochemical deposition to add the material on the substrate. Because till now, what best I can do in powder bed additive manufacturing is the layer thickness of approximately 30 micron, not less than that. While if I use this process, I'll be able to deposit the material on atom by atom level. So nothing can be more accurate than this process if we use it appropriately. Okay, so with this, one last thing. Okay, I am also trying to develop a system for powder bed where I can eliminate the need for overhang. So the conclusion for this presentation, I have discussed about the additive manufacturing processes. I have discussed about powder bed metal additive manufacturing, powder feed metal additive manufacturing, wire arc additive manufacturing, wire beam additive manufacturing, and in the end, I have also discussed about the rapid manufacturing laboratory and the research we are doing here at IIT Guwahati. So with this, thank you very much. Now, if you have any doubt, please feel free to ask.
Thank you, sir. Thank you very much. So participants, if you have any doubt or any query, then you can ask to our speaker, and you can write your query in the chat box.
Please, you can raise your hand, Mr. Arun.
Okay, so Arun can unmute yourself. You can unmute yourself. You have means.
I think Mr. Arun raised the hand.
Just let me check, sir. Let me check. Arun. So Arun can unmute yourself. Okay. Arun, Mr. Arun Kumar. Arun Kumar, can you hear me? So let me check the chat box. If any query is there, then I will. Okay. No query.
If there are no doubts, Dr.
I think so. I think you have nicely explained, sir. That's why there is no query. Yes, sir. I think no query is there. So, sir, on the behalf of my team, I am really thankful to Dr. Sajan Kapil. Sir, you have nicely explained each and everything about the metal additive based manufacturing. So you have covered.
I cannot hear you.
Hello, sir. Hello. Sir, can you hear me, sir? Hello. Sir, can you hear me?
Yeah. Yeah. Now I think I can hear.
Okay, sir. Thank you. So, sir, on the behalf of sir organizing team, I am really thankful to you for sharing our knowledge about metal additive manufacturing. So, I hope the knowledge given by you will be utilized by our participants, and they will come up with new ideas, and they will implement this knowledge in the future projects. So, thank you, sir. Okay, sir. I think one query is there in the chat box. Hello.
I'll read it. Yeah, I'll read it.
Okay.
Okay. So we as we know. Okay, I didn't get the question. I think it is saying, whom do you work for amending the CNC control system to enable 4th and 5 axis? So conventionally, the CNC machines are already along with the 5 axis, for example. So we just play with its kinematics. What we do, we change its TCPM called tool coordinate position management, and hence we utilize this in the CAM package. Then we do the programming by ourselves. We do not take any help from a third party. So if you want to know more about it, you may please write to me. Yeah, we utilize the TCPM. Yes. So quiz timing, I don't know, but okay. Yeah, thank you. One more. Yeah. Okay. You are muted, Dr. Narendra. You are muted. You are saying something, I think.
Okay, sir. So thank you very much for making time for us.
Thank you.
And thank you, sir. Thank you very much. Okay, so dear participants, now we will have next session at 2 p.m. So Dr. Mohammad Tawfiq will be going to discuss about the different aspects of related to 3D printer manufacturing. So he will tell you how to build a 3D printer. Okay, so he will tell you about the different components, what are the different components required for 3D printing, 3D printer, and how can you make your own 3D printer. Okay, so thank you. So now we will meet again at 2 p.m. Thank you.
Okay, good afternoon, all of you. Can anyone please tell me my voice is audible or not? Can you hear me? Any participant, please unmute.
Yes, sir.
Okay, fine. Hello, Dr. Naren. Now this PPT is visible on the screen.
So participants, now we are going to start. So now I welcome again in this session. So Dr. Mohammad Tawfiq from Mainit Bhopal is with us again. So yesterday he has discussed about the design for manufacturing, additive manufacturing, and today he will discuss very important topic, that is build your own 3D printer. So he will emphasize the discussion on the different components that is required for 3D printer manufacturing. So now I welcome sir.
Thank you, Dr. Narendra. Can you see my...
Hello sir, am I audible to you?
Yes, I can hear.
Hello.
Hello. I can hear you.
Tawfiq sir?
Yes, you are audible.
Tawfiq sir?
I can hear your voice.
Sir, am I audible to you?
Yes. Can any participant tell me whether my voice is audible or not? Any participant?
Yes, sir.
Okay, fine. Okay, now I'm going to start this presentation. Okay.
Yes sir, please.
Okay, fine. So in this lecture, we are good afternoon, all of you. In this lecture, we are going to understand how to build a on 3D printer. So quickly, we are going to start this topic. So already we have a lot of people have already discussed with you people that what is the difference between conventional and additive manufacturing processes. For example, these are the conventional manufacturing technique like milling, drilling, press working, welding, and casting. Quickly we will recap it. So in the conventional manufacturing technique, these are the main advantages that we can go for the mass production. There is a good repeatability. Type of material also, we have lot of material. We have already this. We have the more trained staff for this particular conventional methods. But there are some limitation. For example, design freedom limitation we have, low volume production, we cannot go for the conventional manufacturing process, and the installation and tooling cost is very high. So these are the some constraints. So how we are going to cope up with this condition? So there is any alternative? So nowadays people are moving towards the 3D printing. Already we have discussed this one. This is the layer by layer addition technique. We will skip this one. So nowadays this one also, we lot of people, you have discussed this process of the 3D printing, start with the CAD molding and going with end with the post processing. So here what is the thing that in the 3D printing application, if you are going to see, it is applicable in the different sector, from the education to socio-cultural and in the industry. In all aspect we are utilizing the 3D printers. And now nowadays you can see here we have printed the very small jet engine, and nowadays we are also printing the very large buildings. So the variety of 3D printing application is very huge. We can go for very small as well as very high component. Now all we know that there is a broad classification for additive or 3D printing. So here we have the liquid based, powder based and solid based. So in the liquid based stereolithography, powder based, selective laser sintering, in the solid based it is a fused deposition modeling and also known as triple F fused filament fabrication. So in this lecture we are going to more focus on this third classification, solid based additive manufacturing process, where we are trying to understand how to make a entry level fused filament fabrication machine. Okay, so if you are going to see this solid based extrusion technique, that is also known as the material extrusion based 3D printing technique. So there are different way to create this extrusion process. The first process is the pellet or granules base. So what people are doing, they are utilizing these pellets to extrude the material to the heated barrel. Okay, and there is some nozzle assembly here we have, you can see. So in this regard, the basic concept for doing this type of or creating or building this type of printer is that we can utilize the conventional X, Y and Z system from any conventional machine, and simply we are going to install some extruder head like this one. This is the extruder head. We are going to provide on that XYZ system, positioning system. This is the positioning system we have, and simply we are going to provide here the extruder head. So in this way you can create your own 3D printing machine. So here if you are going to see the X, Y and Z all positioning movement provided to the bed here. The same time different type of application we have, either we can provide the XY movement to the bed and Z to the extruder head. Okay, so any conventional machine having the XYZ movement, you can simply convert it into the 3D printing machine. For example, here in place of this is the CNC milling machine. This one is the CNC milling machine. So what you can do simply here, in this field Dr. Narendra have done fabulous work. Nowadays he is working on the conversion of this particular CNC milling machine to a 3D printers. So what you can do, simply you need to replace our CNC milling tool with the extruder. So simply you need to build one extruder. So here if you are going to see this particular assembly, this one is the screw, there is some funnel, okay, through which we are going to fill the pellets, and then we have the heater. We can put heater, see, this is the band heater, you can put here, for the melting of pellets, and then here we have the nozzle through which we can extrude the material. So simply you can clamp here on the CNC machine, and in this Z axis is provided to the this particular extruder head, and through which you can generate your material, and you can complete your 3D printing process itself on the conventional machine also. This is the one method. Okay. Second method to build your own 3D printing machine is the most generalized way that we have in the market also. That is the based on the filament. Here what we need to do, we need to pass a filament from some heated nozzle. So how we can build it, we are trying to understand in this particular lecture. More focus we are going to provide on this particular type of 3D printer. If whenever we are going to see this type of entry level or a small type of 3D printer, okay, we have basically three main components. If you are going to see, one is the mechanical component, okay, other one is the electronics component, and third one is the software part. Okay, so once we are going to combine all these three, mechanical part, electronics part, and the software part or firmware part, we are able to build any 3D printing machine. So we are going to understand it. For example, this is the one entry level fused filament fabrication machine. Okay, here we have. So you can see here from this figure that this is the assembly of the different component. Now we are going to understand all this particular assembly component one by one, so anyone can assemble their own 3D printer. Okay, so for this purpose, what we are going to do, we are going to disassemble first this particular printer and visualize one by one each of its component. Okay, so this is the exploded view at 20% distance of the original. Okay, and then this is the 50%. So see here all the component now we can see in its exploded view. Okay, now what we are going to do, we are going to take this exploded view and we are going to understand all the component one by one. Sorry. So for example, basically we are going to categorize all this printer element with 33 components. Okay, and we are going to start with the, first of all, we have this power supply. Sorry. So this power supply, the name itself implies that to provide the power to all the electronic elements. Okay, so for example, motherboard, control board, and all other electronic elements operates on the DC voltage. Okay, and generally there is a requirement of 12 volt or 24 volt DC voltage. Okay, volt or 24 volt DC voltage. So what we are going to do, so all these electronic element cannot be connected directly to the AC power source. So therefore there is a need of system which can step down the 220 volt, whatever we have, 220 volt to a lower voltage of 12 volt or 24 volt, and rectify this AC voltage to a constant DC voltage. So most of the power supply consists of the series of the screw terminal. Out of these terminals, some are for the input of the AC supply and others are for the output of DC voltage. Okay, so for example, generally we can go for the 24 volt, 15 ampere or 360 watt power supply with cooling fan enclosed in the aluminum cell is widely used in the 3D printer. Okay, After that, we have the second component. You can see here, this is the LCD controller. Okay, so this LCD controller, whenever we are talking about, this is the smart controller, and it is used to interact with the 3D printer without using the personal computer. If you don't have the personal computer, you can usually interact with this particular LCD controller. Okay, need not to means connect with the computer. Okay, you can understand from this particular LCD. And generally this smart controller is consisting of the LED display and some we have the SD card reader. Simply we can put this SD card where we have the G code file can be stored in the SD card. Okay, and from this SD card you can interact. Okay, now if you are going to move with the third one, this is stepper motor. Okay, so we know the stepper motor we are utilizing. You can see from here we have the stepper motor, and we can use the stepper motor for precise and controlled rotation of the shaft, and through which we are going to provide the precise motion to the pulley and belt system. Okay, sorry. So we can utilize this one, this particular stepper motor. Unlike the simple DC motor, stepper motor can't be drove by the directly supplying the DC voltage. It needs some driving, okay, circuitry, which subsequently supply varying current to the wires of the stepper motor. And this varying current, varying amount of the current is also known as a pulse. Okay, and each step shaft of the stepper motor is rotated by fixed angle. By doing so, we can provide a precise motion to the pulley and belt system. Now if you are going to move with the other element, for example this control board, okay, we can also tell it as a motherboard, and it is a board compatible with the microcontroller on which all the peripheral like the stepper motor, drivers and extruder control circuitry can be attached. Okay, generally it is a shield of the microcontroller like the Arduino Mega, but also available as a single board on which control board and the microcontroller both are integrated. Okay, so in the simple way we can say this microcontroller is the brain of the 3D printer. It's listen all the input and sensor of the 3D printer and then process the information received and command the actuator to perform accordingly. Okay, so next one is the next element is we have the limit switch, and this is a very important component of 3D printer. You can see here this is the limit switch. Okay, so this particular thing limit switch we are utilizing in 3D printer and need as a reference location to perform all the movement during the material deposition. To locate this reference location, limit switch are indispensable. We can use at each axis, for example x-axis, y-axis, z-axis, and these limit switches are one type of sensor. In a simple way we can say we sense the position of that particular this bed. Then we are going to move with the other hardware. For example, these are the other hardwares. If you are going to see this much hardware we have, plenty of hardware. Okay, so to fix the wheel with carriage plate and other mechanical component, this simple hardware like the nut, bolt, screw, washer we are utilizing. Okay, we can simply or combinedly explain this. Now the most important thing that we need to learn here is the extruder assembly. This is the very important part of the 3D printer. Okay, whenever we are talking about this 3D printer, the extruder assembly plays an important role. Okay, so we can say it also the extruder is the central component of any FFF 3D printer, and it is very important, you know? And in this particular extruder, we have the mainly 4 parts. For example, we have nozzle, hot end, cold end, and the extrusion drivers. So if you are going to see more in a more detail, okay, for example, this is the view we have seen here. Now we are going to see here the side view of the extruder assembly and the extrusion nozzle. You can see here, this is the nozzle we have. Okay, so this particular nozzle we are going to attach here, attach at the end of the extruder, and through its small pinholes, molten material will come out to deposit on the print bed. Okay, so this nozzle is attached. This particular nozzle, you can, if you are going to see here, it is attached to the hot end. Okay, hot end, and with the help of the screw mechanism, and in this hot end we are going to through this hot end we are going to pass the filament. Okay, so this is the very important aspect. Here we have the, if you are going to see the cooling fan, it will restricting the extra heating of this particular block by which the filament is coming. Okay, so it is maintaining the temperature, because here we have the cartridge heater. It is continuously heating the heating this block, heating block. Okay, and this heating effect, it will not go through the upward direction. We are going to provide some sort of the fan, cooling fan. Okay, please students or participant are requested, please mute their mic. So it will be very helpful if you are going to mute your mics. Okay, so this is the one of the main component of the any. Now if you are going to see, so here the next thing, here we have the LCD back plate, and the name itself implies that it holds the LCD controller on the upper frame. Okay, and then this is the Y limit switch plate to mount the limit switch of the Y axis. Okay, on which we are going to mount here for the Y axis, and then we have the T nuts here. So to hold the Z axis release screw in the motor mounting plate and the pulley holder of the X axis, we require this T nut. And here we have the coupling, you can see. And it is used to couple the Z axis motor shaft with the lead screw for the power transmission. Okay, and then wing nut. It is very important, also very important as a component here we have. So if you are going to see this particular plate, lower plate we have. Okay, so it tied the lower plate with the upper plate of the print bed through this. Here we have the springs. Okay, so sometimes if there is a referencing problem with the wing nut by hello, participant are requested, please mute your mic. So through this wing nut we can adjust the referencing if there is any sort of disturbance in the referencing. Then we have the other very important component, which is known as the print bed. Okay, so this print bed is also known as the hard bed. Okay, so here this hard printing bed is the surface on which the first layer of the extruded material from the metal is deposited to print the part. Okay, so as the material is deposited on this print bed, for example, there is the nozzle and it is start depositing the material. Okay, So once it is going to deposit on the print bed, this particular material starts cool down with the faster rate. Okay. So for example, if it is moving like this, it is going to start cooling. It will start from here and it is moving like this. Okay. So there is a quick cooling of it. So there is a chances of it will solidify, and there is a not proper elimination between the next layer. Okay. So what we can do, for that purpose, we are providing some heating to this particular bed. So it will maintain the temperature of extruded filament, so proper bonding can be happen. At the same time, due to the uneven cooling, it might be possible that there is a curling effect will more pronounced. So to prevent this, there might be some curling will occur like this type of effect. Okay, at the corner it is going to detach. Or to prevent all these things, we are providing some heat to our platform. That's why it is also known as the hot bed. After that, you can see here the print bed spring. On that spring, we have here print bed. Okay. So this print bed spring, through the wing nuts, we are going to adjust the height of this particular. Through the wing nuts, we are going to adjust the height of this particular bed. So we are utilizing this particular springs for this purpose. And then we have the print bed lower plate. Okay. So to attach the bearing, housing, and carrying the hard blade, we have this print bed lower plate. Okay, and then we have the inter-ring locks also here. Okay, to retain the linear bearing inside the bearing housing, we require this. Okay. Similarly, we have the linear bearing for the smooth movement of the print bed and nozzle assembly. Okay, for the smooth movement, we require the linear bearing. And then we can see here the bearing housing carriage. Okay, so this actually the carriage is a component which ride on the linear rails and moves smoothly in one direction and carry the component like the extruder, nozzle, assembly, print bed. Okay, all these things. And then we have the Y belt attachment. Okay, to join the both end of Y axis belt to the closed. Okay, here we have the Z lead screw. This lead screw we have in the direction of the threaded screw. Here we have for the movement of the extruder nozzle along the Z axis, we require this lead screw. And then to maintain, hello, anyone is continuously speaking. So the next component, we have the pulley belt system. Okay, to transmit power from motor to the carriage, we require this pulley belt transmission system. And then we have the Z limit plates to hold the guide, the rail, and lead screw of the Z axis. We require this particular Z limit plate. Okay. And then similarly, we required here the Y motor lock to separate the Y direction motor and fix it rigidly with the frame. We required this Y motor lock. And similarly, the Y pulley holder and belt tensioner we have to hold the pulley and generate the sufficient tension in the Y direction. Similarly, we have X belt tensioner. And then we have the X driven pulley holders. To hold the X direction driven pulley with the frame, we require this one, X driven pulley holder. You can see here. The next one is the X motor mount plate. We have here the X motor mount plate. To mount the X axis motor on the Z axis guide rail. Okay. Similarly, we have the Y motor mount plate to mount the Y axis stepper on the frame. Similarly, we have the Z motors mount side plates, and then we have the Z motor mounts upper plate. So you can see here these are the upper plates here To mount the Z-axis stepper motor on the frame, we require this one. And these are the guide rails. All these are known as the guide rails for the smooth movement of the carriage of extruded assembly, print bed, and we require this. And then we have this the frame rod, and this frame rod we can utilize. This frame rod we can utilize to connect the front frame with the middle and back frame using these nuts and bolt and washers. And this is the final thing, is the frame. Frame here, it is a very important, one of the important component. Frame is the mechanical structure which carry the load of all the other element of the 3D printer. You can see it from this figure also, this frame. So it may be of the steel rod and then the other material also. We can go for the acrylic also. Okay, so basically this structure is carry all the mechanical and electronics elements. Okay, so 1 minute. Now we have, see here, the third element in this particular thing in the 3D printer is the important is the software or firmware. The software is uploaded to the microcontroller to perform all the function of the 3D printer. And this particular thing converts G code into the electrical signals that control the stepper motors. Okay, so here we need to understand, okay, what is the G code. So if you want to go for, before going for the discussion of G code for the 3D printer, okay, the common firmware produced by the RepRev, okay, and we can go for the RepRev firmware for this type of 3D printers. So here we have the general G codes and M codes used in the 3D printers. Okay, so we are going to understand this in detail. So for example, once we are going to see in the last few lecture, you people have learn about the tessellation, okay, some sort of tessellation. Then you people have also know about the slicing. Once you are going to complete the tessellation and slicing, you are going for the tool path preparation. Okay, so how this tool part we need to write, what is the syntax for this type of triple F 3D printer for the tool path. So in this triple F 3D printer we are using G and M codes. Okay, G codes are also known as the proprietary codes, and M is the stand for the miscellaneous. So this is the combination of G and M code. So this particular G and M code is quite different with the conventional CNC machine G and M codes. Those who know about the CNC milling or CNC drilling, all this type of CNC lathe, G and M code, there is a slight difference between this G and M code of the 3D printer and other GM code which we are usually utilize in the CNC milling and drilling and other CNC operations. So for example, what is the basic difference? We will try to understand first. For example, in the actual, for example, if you are going to see, 1 minute, I need to take. So we will try to understand what is the difference between the G and M code for conventional and the 3D printer, and then we will discuss the 3D printer codes. For example, in CNC milling and the 3D printing, okay, both are using the G and M codes. G and M codes. Okay, so if you are going to see in the machining, okay, we are moving in the X, Y, and Z direction. And here, if you are going to observe this 3D printing process, for example, this is the 3D printing process, okay, and here the material is coming from somewhere else, for example, from the spool, material is coming, okay, this is the condition of the material, okay. So one thing we need to understand here, for example, if in the conventional milling, we have the material block, okay, initially we have the some sort of material block. If you need to make a small part, we are going to remove extra material. For example, this is the extra material, we are going to remove it, okay, okay, and we are going to obtain this this internal one as the finished product, okay. But here we need to extrude the material, sorry. Sorry, one. Sorry for disturbance. So here in the 3D printing, actually we need to extrude the material, okay. So whenever we are going to extrude the material to make any part, for example, this is the nozzle we are extruding, na? So what is the basic difference here? We need to calculate the extrude factor here, okay. How much material we need to extrude, that is defined with the E, and this E factor you need to define, because how much material you are going to deposit here. So in this G and M code for the 3D printing, in this G and M code, we have the new parameter we are going to define here, that is known as the extrude factor E, okay. So this particular factor actually differentiate between the G and M code for the CNC milling. For example, in the CNC milling, we don't require any extrude factor. So simple G and M code we are going to utilize, okay. So whenever we are talking about the GM code for the 3D printing, we need to define one new parameter that is known as the extrude parameter E, okay. So for example, now we are going to see this code, so you will understand. Before going to this one also, so here if you are going to see, whenever, so what you need to do, you need to do a small exercise. What you need to do, you need to create your own G code and save it and open it in the notepad and try to understand the E factor. See here the E factor. E is represent the material extrusion capability of that particular pass, okay. What is the length? Based on that you need to extrude the material. This is the difference code we have in the 3D printing, okay. Now we are trying to understand all the code. So this small exercise you need to do by yourself. You need to save your tool path in G and M code and open it in the Word or in the notepad, and then try to understand. So see here, T0 represent the tool. There is a chances of dual extrusion or single extrusion. If it is this particular code written for the single extrusion, okay. So T0 represent that single extrusion nozzle, okay. And then here we have the M140 S60, okay. So these codes are slightly different from the previous what you learn in the conventional CNC milling and turning. So for example, M140 represent the set temperature for bed fast, and S represent this the target temperature what we need. For example, S60 means 60 degree we require temperature. Okay, and then we required some time to report that particular reach to particular temperature M105 report temperature, and then we are reaching that temperature. For example, S90 target temperature, if you are going to write along with S whatever you are going to write, it is the target temperature. Okay, and then M140 is the set extruder temperature. It is used for the extruder temperature. There are two, one is the bed and other is the extruder temperature. So for example, if you are going to put the extruder temperature 200 degrees centigrade, for example, in case of the PLA, we can extrude material at 200 degrees centigrade, so we can set for the different material this particular value we are going to change, and similarly we can change the bed temperature also. Okay, and then again here how the waiting time we are going to wait. This is the waiting time from, for example, from room temperature it is reached up to the 200 degree from 01 to up to 200. M109 it will show the wait till the temperature of extruder reaches the target temperature. Okay, and then M82 represent the absolute extrusion mode. Means absolute extrusion mode means whatever material we are going to extrude for one line and other. For example, we have the 4 line, we need to print this type of object. So here we are going to add the extrusion value. For example, if here 1, for example 1 here also required, then we will write E2. Here 1 also required, E3, like that, E4. Okay, so this is the absolute mode. And then we have the G28 for the home positioning. It will send your printer to the home. For example, in most of the time it is in the left side. Okay, and then sorry, we have, see here in this one, G1 means it is the linear movement, and G1 G15 F some feed value here we have. So here what we are doing, we are moving the build plate 15 mm in the positive Z direction. Okay, with the some feed rate. Okay, why we are doing so? To set a new sorry for disturbance. Now where we are, so we can change the reference plane to set a new reference plane, like what we are doing in the conventional CNC milling operation. Okay, so G92 it's showing the new position. Okay, and the E0 is showing the reference point for the extrusion of the material. Okay. Similarly, you can observe this G1 stand for the linear movement, F is the feed, and E3 is the some amount of the material we need to extrude. Okay, M41. Okay, so if you are going to see here, the set the temperature of the chamber 28 degrees centigrade if this is a closed chamber 3D printer. Okay, then we have the, see here, this is the minus 6.5. Why it is written before? Because we need to ensure before the extrusion of the filament we are trying to extrude back up to 6.5 mm, and then we are going to set as a 0, and then we will start the extrusion of the material. Okay, to simply to confirm it. Okay, whether the correctly 0 are set or not, and then we will go for the simple movement. For example, here in X direction 33 and Y direction 0. In X direction we are going to move something, some amount, for example X direction 33, and here the material extruded to cover this length is the E 1.6464, for example, and then it is moving. Okay, and then next XY coordinate it is moving, and this time this is the absolute mode. So if we are going to subtract from 1.6464 to 1.9117, so you can get the actual amount of the material extruded. Like this we will complete it. Okay, so here if you are going to see in the case of the 3D printing part program, GNM code, okay, whenever we are going to see, always we have the G1 command. And if we are going to remember in the conventional machining process, for the circular clockwise or anti-clockwise, we have the G02 or G03 command like this. Okay, but here generally we are going for the linear interpolation only, G01, because whenever we are going to convert, for example, this is our part, we are going to convert into the STL file. So, and then we are going to slice it. So the small approximation, this is the already very small length. Okay, so the straight line approximation we have already. So generally we are covering this with the G01. Here we don't require generally G02 or G03. So in the all the program you will see G01 command only, and it will utilize to complete all this. It will utilize to write the all these particular codes. Okay. So G0, if you are going to see here one other component, we have the G0. G0 is a rapid movement. Rapid movement, and in this particular movement we are not extruding anything. It is similar to the conventional CNC machining process where rapid traverse we have, and that particular traverse we have the maximum feed set by the manufacturer. At that tool is moving from one position to another position. G01, the linear interpolation or linear movement. Okay, X, Y, Z, these are the values we are going to tell the printer. Now it will move to cover the particular distance. And then we have the some E value, extrusion factor. Okay. So these are the some main concept related to the GNM code. See here G92 sorry, set the value of extruded filament. E represent the new extruded filament length. Even M84 set the idle hold or inactive the steppers. Okay, so here, so what we have seen in the software, this firmware convert G code into the electrical signal and control the stepper motor, and that based on the stepper motor it is going to move your platform and it is going to build the part, or nozzle it is going to move and build your part. Okay, these are the some sort of introduction to how to build your on 3D printing machine. Okay, so here similarly we have the T01. If this is a dual extruder, we can go for the other control tool also, T01 also, T00 here we have T01 we can use in the case of dual extrusion. Okay, dual extrusion means, see here, sorry, see, single extrusion means we are going to extrude only one filament. Dual means, for example, extrusion means we have this Y-shaped channel. Okay, and this through Y-shaped channel we are going to pass one nozzle from this side, one wire from this side, and other wire we are going to pass through this side. Okay, so we will put T0 and T1. Dual extrusion, this particular thing is known as the dual extrusion. And dual nozzle means two different nozzles we have. Okay, here one nozzle but two passes for the extrusion. Okay, so here T01, T0, two nozzle we can utilize. So different classification we have for the nozzle. Okay, and sometime we have two type of classification for the how this particular filament is going to extrude. Okay, so based on the filament extrusion technique, we can tell it as a direct extruder, or we can sometime we can call other technique as a Warden extruder. In the direct extruder, we have directly attached the filament on it. So here we have the different type of nozzle assembly or extruder assembly. Okay. Okay. So here we have this particular direct extruder, some roller assembly required to feed this particular material to the here. In Borden, directly we are going to put on the top. Okay, it will extrude from the nozzle. Okay, so the different type of classification we have. Okay, so main thing is here that this is the how you are going to work with the different type of tool path programming. Okay, and then see here, this is the code for dual extrusion T0 T1. Okay, so this is also we have. Okay, so different type of application we have in the field of additive manufacturing. Based on that you can apply it. Okay, so those who are more interested to learn about how to make your own 3D printing, please note down this paper. This paper is published by myself in the Elsevier. So you can write down, and this is the DOI. You can write down it and then download for the further reading. Okay, and if you people have any further query regarding this particular thing, you can please note down this email ID where you can connect to me. Okay, so now with this I'm going to stop my presentation here. Okay, so anyone have any doubt, so please ask, otherwise I'm going to close this session.
Thank you, sir.
Thank you.
Dear participants, if you have any doubt or any query regarding this lecture, then you are most welcome to ask. So our speaker is there, so you can write your query in the chat box either, or else you can unmute yourself and you can raise your query. Thank you.
Okay, might be there is no question. So, okay, Dr. Narendra, can I leave? Dr. Narendra, can you hear me?
Sir, let me check chat box. I think some query I think is there. Yes, sir. One participant asking about the G codes. G codes, different OEMs use different standard. Okay, I think he's asking about the difference in the G code that is generated by the different OEMs or the different controllers. So kindly share.
Okay. So in see, listen, the two different thing. If you are going to see with respect to conventional machining, we don't have this E concept, extrusion factor. So please remember one thing, whenever we are talking about the G and M code, don't confuse with respect to conventional CNC milling machine or turning machine codes. They don't have that particular E in their programming. Okay, here we need to define the E. E is the material extrusion factor for particular length. Okay, and then after calculating this particular material extrusion length, we need to add it into in a G code. So in all the G codes, whatever G codes we are going to generate from any firmware software, it will always contain, if it is a extruder based process, it will contain the E and G1, a linear extrusion. These two things always be there. Okay, please remember, don't confuse with this particular code is not applicable with the other 3D printing technique which is based on the liquid or powder base, because there we are utilizing the laser. Their code, the way of the code writing there is different. This is applicable for the fused filament fabrication machine. So most of the fused filament fabrication machine, if you are going to open it, only I am talking about the freeware software. Okay, you can simply understand, and you can, for example, if you are going to save in the Cura and open the Cura codes. Cura is the more popular software in the field of 3D printing. So if you are going to check with the Cura, you will get the exact matching. Okay, and the other code also, they are similar if it is written for the fused filament fabrication machine, and this code is not applicable for the solid.
Sir, I think there is another query in the chat box. So, hello, sir.
Yes, sir. Please.
Tawfiq sir.
I can hear you.
Sir, please see our chat box. Chat there. So please answer the query.
Chat box.
Tawfiq sir. One query is there in the chat box.
I'm unable to see that chat box.
Okay, I'm just telling you. Let me check. Okay, is there any standard body to consolidate it?
What? Pardon?
Is there any standard body to consolidate it? Assembly means asking. I think he is asking about the assembly. Means if you have different parts with you, then
so
how?
Listen. So in the in the generalized way, if you need to know how to build any 3D printer, you required only three things, main things. Okay, one is the positioning system. Okay, and the supporting means all the electronics component, basically having that particular thing. What I tell you, that all the positioning movement systems, and then we require the frame and all the mechanical component, and third one is the firmware, okay, software to execute all this thing. So basically we can classify. Can you see this particular slide?
No, sir, I think he asked about the method of assembly. Is there any standard procedure to assemble all the components, or just like that we can assemble any component with any company?
So listen, the assembly of the FFF 3D printer, whenever we are going, the load carrying structure is the frame, which is the first to assemble, and then various other parts could be mounted on this frame. Okay. Okay.
Okay, sir. So thank you, sir, for your valuable time.
Thank you. Thank you, Narendra.
So dear participants,
so I'm leaving this now.
Yes, sir,
I
yes.
have the other meeting, so I am going. Okay, thank you.
So dear participants, tomorrow we again meet at 10 a.m. So in that lecture, I think Dr. Bera from NIT Durgapur, he will be discussing some electrical based application of 3D printing. Okay. So thank you for your time and your patience. So thank you.